YOLO.
All right, I think we should be good now. I think it looks like it's picking up. Hello everyone, how are you all doing? We're just checking the audio now to make sure everything's going okay. My name is Brendan. I'll be running through the first part of this revision seminar today, and we're also joined by Tom, who's just outside checking the audio for us to make sure everything's going good. So how was it? Good? All right, so we might get started then. Just give me 1 second to put my laptop in charge. So as I said, I'll be running through the first part of this revision seminar today. So for those of you that kind of like me, left this course on the back burner for 3 or so weeks, this is a good chance to revise everything that we've learned so far. In particular, I'll be taking you guys through the first 2 topics. So that was everything examinable. Yeah, okay. That was everything examinable within the first class test. But we'll be looking at a few things that weren't examined and revising a few things that were. So let's get started on that. Let me just check how this all works first of all. I'm just new to this system. How do I... Wait, that's good. How do I change colors, Tom?
Good question. I
Oh, what the heck? Did this like wrap out this one?
I don't know what those do. Like, I don't know if it erases or something.
Oh,
If you want like underweights, they just do like Control Z or something.
oh, fair.
Oh no, not a good
Oh
book.
no.
That was
Okay.
good enough. Good.
It's I could be the best. Okay.
Minimize errors.
Oh, okay. All right. So let's get started then. So wait, how do I change colors? Hold up.
But I mean, you're just gonna have to like do it manually. So like when you're like writing stuff, like press the dots and then like just
No,
do these manually.
I'll just stick to red then.
Okay.
All right. So yeah, first topic. Let's go through this. This is linear ODE. So hopefully this is a lot of revision for you guys, not only from Math 1B, but also from let me get to this, but also from the first topic of this course. So in looking at linear ODEs, the first thing we can look at is kind of before a linear ODE, we looked at as well this first type of simple ODE that we can solve, which is called a separable ODE. That's when we can write the derivative of y is the product of a function of our independent variable t and our dependent variable y, right? So we have it somewhat like this, which then allows us to go forth and, as we would say, separate the variables. So bring this y down, sorry, let me draw. Just like that.
Yeah.
Oh, and then I go draw. Yeah, sure. Oh, it's so thick.
No good.
Desperately need.
Wait, you can use the thing to rub out, right?
I think so. That's the bottom one.
I mean,
What
oh, it's like a contour. You have to like grab that and like, yeah.
Okay, sure. So scuffed. I need to change the thickness. No, I got it.
Okay, just like stick it like one thickness. Hopefully.
I think this should be, yeah. We're sticking to this. Alright. What? Why is it so big? What the heck? Okay, we can live with that.
Yeah.
I might decrease it a little bit then. Okay. Alright, that's good enough. Moving on. So that's a separable ODE. And now let's look at the next thing that we want to look at, which is this nice case of a linear first order ODE. So this brings up a technique known as the integration factor method to solve this, which comes up many times in this course, not only in this case of solving linear ODEs, but also in writing equations in self-adjoint form, which we'll see later in, I believe, topic 3. But for here, what we can do, if we have this type of differential equation, is we kind of force it to abide by the product rule. So we multiply it by this integration factor, this little mu here, sorry, up here, such that when we multiply that to both sides, what we can do is write the equation as mu of mu times y, or the derivative of that, and that setting that equal to f, okay? Oh, f times mu, right? So I'm just getting used to the triangle, obviously, not my strongest suit. And then doing that allows us to chuck in the derivative on the other side, so that we have mu times f plus c, and we're dividing by mu to get rid of that, okay? So a simple example here, what we can do with this, first of all, what we need to do and what you have to remember in cases like this is you always need to make sure that you don't forget to write the equation in this kind of normal form which we have here. Remember the equation over here, we need to make sure that we have y dash having no coefficient in front of it, otherwise it doesn't work out in the way that we want. So first of all, we'd have to write this equation in the way y dash plus 1 over x ln x times y is equal to 2, we're dividing by ln x again, so 2 over x. So our integration factor here would be e to the integral of 1 over x ln x, which I hope that you can verify will just be e to the double ln. Let's not worry about I should have the absolute value signs here. And then the plus c, we don't really care about. We can just get rid of that. We don't really, let's just say plus 0, because we can choose our constant to be anything. Hopefully remember that's something we discussed early on in the course with Chris. And so this becomes ln x. And so we can write this equation as ln x. I should keep the absolute values. The derivative of this times y is equal to 2 ln x over x, right? And then what we would say that y is equal to 1 over ln x times the integral of 2 ln x over x, which this integral turns out to be, let me just scroll down a little bit. This integral turns out to be 2 ln squared x plus c, and we're dividing that by ln x, so this is what the solution would be for y, okay? So hopefully that's pretty nice for you guys. Now some more definitions. We look at this idea of kind of making some more nice notation for dealing with derivatives and think of them as linear operators, right? So those of you that have done a little bit of linear algebra this term, hopefully are familiar with the idea of a linear operator. That's something that respects addition and multiplication. So we can split it up when we're applying it to a sum, and we can drag out scalars when we're applying it to scalar multiplication. And so what we would say that L of x here would be is we're applying this type of polynomial in this d, which is the, or d to the power of I, we say is the ith derivative of u with respect to x. That's when we're applying d to the power of u, that is. But we would say like kind of d is more generally like dj over as an operator. And then when you apply it to u, then you get this u here, right? So it kind of grabs in u. So it's the derivative, you may remember, is a map from thinking about vector space as one space of functions to another space of functions. So that's kind of what we're working at here. And then if we combine a bunch of these different maps together by adding them up, since the derivative map itself is linear, and second order and third order derivatives are also linear, if we have a polynomial with these types of functions, a m minus 1, a mx, and so forth, then the total thing would be this linear L here, okay? All right, And a little definition is that we said that ODE is singular in this in a particular interval AB if the leading coefficient vanishes at any point. So for example, this differential equation will be singular on 0, 1 because when x is equal to 0, the leading coefficient, which is x, becomes 0. All right. So we prefer non-singular ODEs because they're nicer to work with, whereas when we have singular ODEs, they become problems, particularly when we're dealing with parallel series, as you hopefully remember from the Frobenius method. And say with the Cauchy-Schwarz equations, we have to do a bit more work when we're dealing with singular ODEs. Okay. Right. So moving on, we have these two definitions. So if you remember, homogeneous differential equations is when you have the linear operator, and the equation is written with the right-hand side being 0, whereas inhomogeneous right-hand side is non-zero. Okay, so some little examples here. Okay, so hopefully those are pretty nice for you guys. And then initial value problem is just when we have initial values and initial information, if you will, that give us kind of enough to be able to get a unique solution. So we'll look at theorems on uniqueness in, I think, really just the next slide, but this is saying that an initial value problem is where we have this differential equation, linear differential equation we've talked about, together with some initial data, okay? Well, I guess the differential equation doesn't have to be linear. We really only look at linear ones in this course besides those separate ones we looked at the first slide. But yeah, initial value problems can also be, I guess, nonlinear. That's fine. But that's when we have, at a specific point A, values, initial values for derivatives up to the order of the differential equation. Because remember, the differential equation has the highest derivative being m, we typically say, okay? So coupling these together is an initial value problem. And down here we have an example where we have this differential equation with this initial data. And it has a unique solution, e to the negative x, which I hope you can verify. And speaking of unique solutions, we have this theorem which says if f is a really nice function, in this specific case we need f to be continuous. So if f is continuous, then this differential equation has a unique, this linear operator L is non-singular on an interval AB, then if we have that initial data, that initial information, that encodes a unique solution for us, which is what we really want. Okay. And so what does that mean for the homogeneous equation where we don't have that initial data? So if you're kind of familiar with the idea of an isomorphism, you can think about how this theorem, relating it to the case where we don't have initial data. If you remember the kind of proof Chris gave on the lecture slides, that means that the homogeneous equation, the solutions to those form a vector space of dimension m, which is quite nice, which means that our general solution to our homogeneous equation can be written as a linear combination of functions, linearly independent functions, that is. We'll define linear independence in just a second. But a linear combination of them, right? So we would have, say, this type of basis for that solution space, and we write the general solution. Remember the general solution, you put scalars in front of them, okay? So hopefully you remember that from class test 1, working with that. If you want to remember kind of the proof of this, it's quite nice, so have a look at that in the lecture slides. It uses a bit of linear algebra, which we quite like. Right, there we go. Oh, don't jump too many slides. Okay. Yeah, so that's what it said. Yeah, so if you have a basis, you can get the general solution by taking a linear combination. And then for the particular inhomogeneous equation, that's when we don't have this LU is equal to 0. When we have a particular inhomogeneous equation, what we have to do is first find one particular solution, and it's going to often be a bit hard, and there's a number of different methods we can use. We can use like the undeterminate coefficients where we guess a function that kind of works and then work out what the coefficients are. We have, I think, a theorem on that later on. And then if we combine that with the homogeneous solution, then we get our general solution. Because as you may remember, any two particular solutions to the inhomogeneous equation differ by a homogeneous solution. Because if you have LU is equal to F and LV is equal to F, then the difference, LU u minus v, because it's linear, would be f minus f is equal to 0. So this difference of the solutions to the homogeneous, inhomogeneous are solutions to the homogeneous, right? So that's why we have to add these kind of constants. That's kind of similar to why when we integrate, we have to add the plus c, right? Because kind of the difference between all antiderivatives is a constant in that case. Similar type idea there. Okay, so there's this little theorem here where we are looking at a special case of a second order ODE where we're given one solution that is not the zero solution, as in to make it the solution space we can form by that one solution be one-dimensional and not zero-dimensional, which you would get with just the zero solution. Then we could find another linearly independent solution by this formula, which looks at multiplying a function to our original homogeneous function, right? And this is quite a nice formula because I guess, well, it's quite nice that Q doesn't really show up here because it encodes the information for that. So just keep in mind this formula. I don't believe yet this formula is not given on the formula sheet you'll get in the exam, because in the exam you'll get, for 2221, you'll get a sheet with some nice formulas. I'll point out the ones that you do get, but this one's not on this, so you might want to keep in mind the kind of proof for this if you want to derive it on the spot or just remember it. Okay, so this is kind of a big scary theorem. Hopefully you remember kind of what it says though. So what we're saying here is that if we have an inhomogeneous equation with now the constant coefficient case, which is kind of the main one we look at in this course, then we can write our general solution as a linear combination of these types of functions. So this here, first of all, we have e to the lambda x. So what lambda is, that's the root of the characteristic polynomial of our differential equation. So what our characteristic polynomial is, if we have our differential equation like this, dn minus 1 and then dot, 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 then our characteristic polynomial would be am r to the m plus am minus 1 r to the m minus 1 plus dot, dot, dot. So we're just replacing our d's with r's in this case, okay? And this is a root of it, and we say that e to the lambda x is a solution. But for the cases where we have repeated roots, we want m linearly independent solutions, right? So we want to get from kind of every single root one valid solution. And so what we have to do then, if we have repeated roots, is we have to bump it up by a factor of x. And it turns out that quite nicely that does in fact work out here, okay? Yeah, and these are just our constants. So hopefully you recognize what this means. If not, just review the slides. But hopefully you've used this in practice. And so we can use an example here, kind of working backwards. So in this case, we have e to the 0 for this one, and then e to the negative 2. So like lambda would be negative 2 for one, and then we're bumping that up by a t here. So another root would be e to the 2. So our differential equation would be, well, our characteristic polynomial would rather be this. And so our differential equation would be replacing the r's with d's, kind of moving backwards, this equation here. And you can kind of expand that out and express it in terms of, oh yeah, I should have the u here. You can express that in terms of d cubed plus 4d squared plus 4d is equal to 0 when we multiply that by u. So that's u triple dash plus 4u double dash plus 4u is equal to 0. Okay, and you can kind of work backwards to verify that that is in fact correct, as in it gives this solution. Okay, all right. Now, precisely defining linearly independent and linearly dependent functions, we said that they're linearly independent if we have any linear combination of the set of functions we're dealing with, these set of functions here. If we have any linear combination and we set that equal to 0, then we only get the trivial solution if they are linearly independent. Whereas we have non-zero constants if they are linearly dependent, okay? So with linear dependence, that's when we're saying there's a dependence of one of the solutions on others, right? So we can write one of the solutions as a linear combination of the others, whereas in linearly independent, that doesn't occur, right? So with linearly independent, then we say we can form the general solution by taking a linear combination of them if we have m of them, right? So, because that forms the idea of a basis, which you'll hopefully remember from Math 1b. And in terms of finding out whether or not they are linearly independent, we have this kind of framework of the Wronskian, which is what we get from, for our kind of solutions, U1, U2, U3, dot, dot, dot. In each column, we put in U1 in the first row, U1 dash, U1 double dash, as in derivatives increasing going down the rows. And each column is a different one of these functions. Okay. So that's what the Wronskian is. And it turns out, the Wronskian is actually the determinant of this matrix, And so it turns out that this Wronskian determinant, there's some nice properties regarding whether or not it's zero and whether or not these functions are linearly independent or dependent, okay? So we have to get a bit precise because it's the kind of original version of the function. The theorem is a bit tricky to work with, but when we're dealing with the main case here, yes, Thomas, question?
Can the Wronskian be negative?
Can the Wronskian be negative? Sure, it can be negative.
Because like when wait, determinants in general, like for linear, they can be negative, but like
yes,
it's like the same for Wronskian.
Yeah, it can be negative. Yeah. Actually, no. Oh, in perhaps a more general case, they can be negative.
Yeah.
Oh, yeah, but looking at this theorem now, there's this theorem here, which tells you, in this specific case, when you have the Wronskian of solutions to a differential equation, then it turns out that the Wronskian has to satisfy this differential equation. So you would say W dash over W is equal to, assuming we're non-singular. Yeah, let's just assume we're non-singular for a second, is equal to AM over AM minus 1. So that would mean that W equals to e to the integral of AM over AM minus 1. And so, it can be negative because this will be absolute value. Yeah, so it can definitely be negative in the general case as well. Well, the less general case where you have them as solutions to the differential equation. It just matters more whether or not it's zero or non-zero. Okay. So looking at this theorem, what this would say is that since this exponential here is always positive, you would have to look at your initial conditions in this differential equation, because I guess I could write this as a times e to this integral if you're solving this differential equation, which the Wronskian has to satisfy if you're slapping in solutions to your differential equation. So you have either two cases. Either this initial a is going to be 0, or the Wronskian's never going to be 0 because this exponential is always positive here, okay? And you can kind of interpret that like the 0 case is a valid solution to this differential equation because kind of here we were assuming that we could divide by W. And the reason why we could divide by a minus 1 is because we're saying we have a non-singular equation. So this kind of is more general than this one. So we're kind of assuming in this case we get this solution up here, which you can see in the lecture slides, when we can divide by a n minus 1 when we have a non-singular equation, as in, it should be divided by am, jokes. Yeah, divided by am. Because if we're non-singular, then am is never 0 in our interval. And it turns out that when the Wronskian is identically equal to 0 on our interval, when we're looking at solutions to a differential equation, then kind of like how if you look at the determinant of a matrix, when it's 0, the column vectors are linearly dependent. So that's the same kind of idea here. The functions are linearly dependent when the Wronskian is 0, and they are linearly independent otherwise, okay? So you may want to review kind of a bit more precise theorems on this in lecture slides, because this is just the specific case when we're slapping in solutions to the differential equation, whereas in general, you have to do a bit more, working with the functions themselves to determine whether or not they're linearly independent by working with the kind of definition we had up here. Whereas when you're working with this case where you have, solutions to the differential equation and non-singular ... it works out nicely here, okay? All right, so moving on. don't really worry too much about this slide. All we're saying here is that when we're trying to find the solution to the inhomogeneous equation, what we do is if we have a polynomial on the right-hand side, then we guess a polynomial of degree r, assuming that our characteristic polynomial of our equation is has a non-zero constant term. And we can do the same thing where we have a polynomial multiplied by an exponential. We can do the same thing, a polynomial of degree r multiplied by that exponential. And you may ask what we do in a bit more of a general case, and I think we have that on the next slide, or there's an example on the next slide, and then it's afterwards. So let's go to that. Oh yeah, before that we also have the annihilator method, which hopefully you saw in class test 1, which is what we do. Kind of a different way of solving our differential equation, where if we have LU is equal to F, what we can do is multiply both sides by another linear operator, MD, like of the derivative D, that annihilates this function f, and so we would have it that MDLU is equal to 0, okay? And if we can find the solutions to this homogeneous equation and take away the solutions to this original equation, the original homogeneous equation, LU is equal to 0, then that would give us the type of form that we were looking for the solutions to the inhomogeneous one, and then we would have to use that process of undeterminate coefficients to work out what it was. If you don't remember what undeterminate coefficients was, just revise that. That was just when you have the type of structure of your inhomogeneous guess, and you work it out by plugging it into the differential equation itself. So look at some revision questions on that if you're unsure, and you can just look at this here for type of form you might want your annihilator to be, and hopefully you kind of pick up as you go what some examples can be. Okay, so this is the more general case we spoke about on the slide before. So now we're saying that if for our root of our characteristic polynomial, mu, if the characteristic equation has mu's not a root of the characteristic polynomial. Mu is going to be mu is going to be here in our differential equation. And so we're going to say that if we're trying to find the particular solution to this inhomogeneous differential equation, where we have each of the mu x multiplied by some polynomial of degree r, then all we have to do is we have to kind of bump it up by looking at a polynomial v of degree r as well. And this type of guess we also made on the previous slide, where we also have each of the mu x, but we have to bump that up by x to the k, where k is the kind of the height, or the reverse height. It's the natural number such that all derivatives of p before order k are 0, whereas the kth derivative is non-zero at this point mu, okay? So kind of that's the deal with the case where we have overlap between the homogeneous solution and our inhomogeneous guess. So that's our kind of cope method with that. We bump it up by this x to the k factor. And hopefully you kind of have the intuition behind that as well. If not, just review class test 1. And then this one here is also on the formula sheet for the final exam. So don't really worry too much about memorizing this one, but what we're saying here is that if we're lucky enough to be given the solutions to this linear differential equation of second order of the homogeneous equation specifically, and then we want to solve the inhomogeneous one when we have an f on the right hand side, what we do is take almost a linear combination of those two solutions, u1 and u2, but we, instead of constant coefficients, we multiply them by functions, and it turns out we can quite nicely work out what these functions are through here. So you'd have them related by the Wronskian on the bottom, our function f, and these two u1 and u2, and it turns out quite nicely that p and q aren't even involved here. And you also need to make sure that you make 1 as the coefficient of u double dash, because you don't want to make a mistake like me and forget to kind of normalize your equation into the form that we want, right? So that's a common idea. Make sure your equation is in the form that we want to apply these, or in this case, the variation of parameters method, and also say the integration factor method. You need to do kind of the same thing to apply the integration factor you need to make sure that the coefficient of u double dash is 1, okay? And hopefully you guys remember this as well, the power series solution method. So this one, with this power series solution method, what you do is, first of all, there's a bit of groundwork here and working out when one exists. You don't really have to worry about these theorems too much, but what we can do is, similar to what we talked about before, we kind of normalize the equation to get that u double dash plus p u dash plus q u is equal to 0 again. So if we have a differential equation like this, then writing p and q like that, if p and q are analytic around 0, meaning that they have a power series expansion for some given radius of convergence, if that works out quite nicely, then we also have, if we try to use a formal power series and work out kind of a recurrence relation for the coefficients, then we also get a solution u that is also analytic as in it has a power series solution, and it converges for this radius of convergence rho as well. Okay, so that turns out quite nicely in this regard here. Okay, so in practice, you don't have to worry too much about when it does exist, because you'll just be given really nice functions to work with. Okay, so this here might be a bit more interesting. So this kind of gives the groundwork for applying the power series method to a case of a bit more of an interesting example and method, which is called the Frobenius method. I'm just checking something here, which is what we, the Frobenius method is what we can do when this kind of theorem we looked at on the previous slide doesn't really work out, as in where we have to do a bit more work to get a series solution, not necessarily a power series, because we might have, as you hopefully remember, non-even powers of z. And so to work with that, we first need to look at the Euler-Cauchy equation, which is what we do to kind of approximate some sort of types of equations near our, or x equals to 0, so that we can find a root of what's called the indicial equation that lets us to work with the Frobenius method. But specifically here, when we're looking at the Cauchy-Euler equation, that's a nice one where as we increase the derivative, our power of x multiplying our u is also increasing. So say here with the constant, it's just x to the 0, then it's x squared, so it's going up. So by looking at the solutions here, what we do is kind of guess x to the r, and it turns out this works out quite nicely because we get a polynomial of degree 2, just a quadratic, which has solutions, okay, like this. You can solve that to find what the solutions would be, and it's a bit complicated when you have, say, complex roots, but in the simple case where you have two distinct roots, r1 and r2, then what the solution will be, just a linear combination of them. When you have a repeated root, then similar to how in the case of constant coefficients, we bumped up by a factor of x, here we have to bump up by a factor of ln x. And then finally, in the case of complex roots, what we have to do is, well, we know that the solutions would be x to the alpha plus beta I and x to the alpha minus beta I, right? And you can kind of write this first one as x to the alpha times cosine, sorry, that's wrong, times, e to the ln beta I, e to the ln beta I, which is equal to x to the alpha cosine ln beta I, and that's kind of how this one shows up, and then x to the alpha sine beta I. And because they are conjugates with this one, you can just take the real and imaginary part of that, and they would be distinct solutions. So that's similar to what we do in the complex case for constant coefficients as well. We take the real and imaginary parts of, say, the e to the I lambda, or e to the real plus imaginary I in that case as well, okay? So hopefully you guys remember that. Just revise on your use of complex roots in the Euler-Cauchy case and the constant coefficient. So now an example here. So in this case, let's solve the homogeneous part of this Euler-Cauchy equation first. So we would get the indicial equation is r squared minus, sorry, no, not r squared, r times r minus 1 minus 2 r plus 2. So that's our integral, so that's r squared minus 3r plus 2 is equal to 0. R minus 2 r minus 1 is equal to 0. So our roots are r is equal to 1 or 2. Okay, so that seems fine. So our homogeneous solution would then be some constant c1 times x plus some constant c2 times x squared. And so looking at the inhomogeneous part, we see there's no overlap just yet with these two sides. So we're looking quite nice. And then the reason why I've kind of brought this up is because it's something you might not have looked at yet with trying to deal with the inhomogeneous case of this equation. So you can use that variation of parameters method we looked at on a few slides ago. So you can use those big ugly formulas and that would work out here. However, a perhaps better method is to recognize that this function on the right-hand side has a similar shape and kind of structure to what one of the solutions could be for this differential equation. So that motivates me to kind of take a guess that we want, in this case, what we want is cosine, a times cosine ln x plus b times sine ln x to be our particular solution. So let's call that yp, right? So that's what we want. And remember our differential equation, if we go up, was that one up there. So we can write this out. Let's call this this here y1, and let's call this y2. So if we write this out, we would get u p dash is equal to 8a times, or negative a y2 over x plus b y1 over x, and up double dash is equal to negative a y1 over x squared. And you can verify these calculations if you want. I've just done them in advance to not have to repeat too much. Plus b, and hopefully we'll see that these x terms on the bottom and these x squared terms cancel out with the coefficients in front in our differential equation. That's kind of what we're working towards. This would be y1, so negative b y2 over x squared plus b y1 over x squared, and this will always be negative jokes. Okay, so substituting this in, we get that since x squared times, was it y? Yeah, x squared y double dash minus 2xy dash plus 2 is equal to 0. I believe that's correct. Let's just double check. Go away, please. Yep, that's correct. Okay, and we need this to be equal to, that, I guess I shouldn't have said the equal to 0 part. We need this to be equal to cosine ln x. All right, so substituting that in, we get negative a y1 plus a y2 minus b y2 minus b y1 is equal to negative 2 b, no, not equal to. Let's move this over here as well. Minus 2b y1 minus a y2, oh, plus 2a y2, and then plus 2a y1 plus 2b y2, and we need this all to be equal to this right-hand side, which I've defined as y1, okay? So that gives us a nice equation. And then because these two functions, the y1 and y2 are linearly independent, then we would say that, say, 1 is equal to this negative a minus b minus 2b and then plus 2a, right? So grabbing all the coefficients of y1. So that's one part of the simultaneous equation, and you get also another simultaneous equation by looking at the coefficients of y2. So say you get 0 is equal to a minus b plus 2b plus 2a, okay? And then solving this, you can go ahead and solve it if you want. I'm not particularly concerned with doing that here. You get your solutions A and B, and that will give you a particular solution to your differential equation here. Okay, so hopefully you can go forth and do that. Yeah, so hopefully you see kind of the pattern here. If you want a bit more of an exercise, you can also try to do the same thing. If instead f was equal to, say, x to the 5, try to do that. Try to see kind of the pattern we're developing here, or try as well f is equal to x, which has a repeated roots case, so you might have to do a bit more work in this case. So think about how you would do some of those. But we'll move on now in the interest of time. All right, so I think the last thing here on topic 1 is now formally defining what our Frobenius method is. So if we write our Frobenius method like this, so our equation is x squared and z squared u double dash z p of z, and then q, so defining our p and q like this. That's what we would say is the Frobenius normal form, so make sure you write your equation in this way. And so what we say as kind of z approaches 0, or z is near 0, we approximate our equation with using p naught and q naught as what p and q are at 0, so this is equal to p of 0, q of 0. Then what we say is that z squared times u double dash, what we have plus p naught z u dash plus q naught u is approximately equal to 0. So that's our approximate differential equation. And it turns out doing this approximation and the solving to get that same integral equation here to get roots, approximating as an Euler-Cauchy equation, does actually work and gives us kind of the foundations of this structured series solution where we have z to the r outside and z to the k, kind of a normal power series multiplied by it, kind of with that variation of parameters type idea, right? So z to the r being the Euler-Cauchy solution, and then multiplying that by a power series. Doing this, hopefully you remember a lot of examples from class tests and practicing, does actually work out quite nicely. Okay, so for practice questions, please look at some of the class test solutions, but hopefully you guys get the idea there. Okay, so we're looking good at time. On time, we'll try not to keep this too long. So now we're looking at the next section, which is on dynamical systems. So this is where we are kind of still looking at linear ODEs, but in this case, we're looking at multivariable ODEs, specifically with solutions which are vectors. Okay, and it turns out that these are quite nice when dealing with, hopefully remember, with higher order differential equations and then vector equations with matrices involved. To get a bit more precise, what we say is that if we have an ODE system, like this, where we have some vector field f. So f is a vector field. It maps from the real numbers to the power of n, as in the Cartesian product of the real numbers n times, being the Rn type idea, where we have n components in our vector, to that same space. We are saying that as x changes with time, so time is a different variable to all these components of x. So we're saying x is like x, y, z, dot, 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 or maybe x is equal to like x1, x2, and so forth, right? Then as they change with time, what we'll look at here, like the derivative, this will be dx1 over t, dx2 over t, right? The derivative, taking it component-wise, will be equal to this function of our current position, right? And so what we would say is that a trajectory is being a solution to this differential equation for x is a curve in our phase space. So hopefully you remember your phase diagrams. That's when we kind of draw out all these different components, our x, y, z. And then solutions to that would be going in the directions of our arrows at each of those points in that space, right? So what we would say is that if we plug in our position, that it always points in the direction of the speed, assuming that we have an equation like this, which is the right-hand side is independent of time, only depends on what our position is. We'll kind of talk about why that's valid to just look at this case in a second. But hopefully you recognize this. And the magnitude of our f, which is like our velocity of our current position, given that it gives this derivative with respect to time, we would say that the magnitude of f is our speed currently, okay? So hopefully you guys see the usefulness of this. So moving on, we have two kind of different cases, so autonomous and non-autonomous systems. What we say an autonomous system is where our system is independent of time. So that's what we had before. There's no time on the right-hand side, whereas non-autonomous is where we have a t here. But it turns out, like in kind of theoretical terms, we can just replace this t with just like a xn plus 1 and then say, well, if we add that to our current x, the derivative of this would just be the same as what we had before, which is the f of x and then n plus 1. And then we just have this as well, 1, right? So what we would say is it's just the same thing if we define like a vector y now and then have this as 1. That's our new, like a new differential equation of dy by dt, and now it's independent of t if we kind of replace t with one variable and then talk about it in a kind of different way now, okay? So in theory, we only have to care about the autonomous case. So you can see kind of the same thing Chris did in the lecture slides for that. So now talking about what we need for one of these dynamical systems to have a solution. We need this idea of Lipschitz continuity. So I don't expect really any questions on this in the final exam, but it's good to have it in the back of the mind if you just need to apply the definition if it ever comes up. So what we say a Lipschitz constant is this constant L such that we're kind of emulating the mean value theorem a little bit. We would have that the magnitude of the gradient line for this kind of single variable function is always bounded by some L. So the function is behaving nicely. It's not going to kind of dilly about too much. It's not going to propagate and fly away and be unreasonable in certain respects in this precise way. So if we have this Lipschitz constant L, then we know our function is nice enough, and we'll see in a sec the theorem on that. And it turns out, for those of you familiar with uniform continuity, that's a bit of a stronger form of continuity, where instead of you having for epsilon there exists delta, you're saying for a specific value of x naught, you're saying for all x naught and given epsilon there exists a delta, so it applies for all x naught. You might want to do that if you want to. And then kind of a little bit of the converse, not exactly the same thing, is when we have if a function is continuously differentiable, then it turns out that it is Lipschitz, right? So first way we have if it's Lipschitz, then it's uniformly continuous. Otherwise, another little theorem is that in kind of the reverse direction, we have if it is continuously differentiable, then it is Lipschitz. By this is just saying applying the mean value theorem to kind of look at this quotient and say that it's bounded by the maximum of the derivative, right? Because you remember the mean value theorem, you have your f dash of c on the right hand side, so it works out like that. All right, moving on. So yeah, we can define the same thing of a function being Lipschitz if it's a vector field function. So we say that a vector field is Lipschitz on a specific set S, which is a subset of Rn. It's Lipschitz if it satisfies this kind of same criteria where we just do the same thing, now replacing it with vector norms instead of like the absolute magnitude, because we're looking at kind of the magnitude of the difference in our function between 2 points compared to the difference in between 2 points, and we're saying that's bounded now by another constant L, right? And what we can also say is that if we have a function of this position and time, then we say it's Lipschitz if it holds for all fixed time values. So that would be saying it's Lipschitz in x if we would have f of x t minus f of yt for fixed t, but it also works for all fixed t, less than or equal to L x minus y, right? Okay. Cool. So in terms of existence, now we can apply this idea of Lipschitz. So if our function is nice enough, if it's Lipschitz on a specific set where we're looking at kind of, if you remember, if you've done rather, 2111 is kind of this ball type idea with a distance from our initial position less than or equal to r, so some sort of radius, and our time bounded by tau, then for there is going to exist a unique solution for time also bounded by tau and kind of bounded by this kind of weird quotient of the radius, given that our function is Lipschitz and is bounded in this type of way. So if it meets that criteria, then it turns out we have a unique solution that's continuously differentiable, which is quite nice for us. Okay. Cool. And so now looking at really the types of equations we care about, where we have pretty much matrices as our function f. So these being the linear ones, whereas previously it may not have been linear. So here we have the linear first order systems where we have the derivative is equal to some vector field, where specifically it's written in this form. So some matrix multiplied by our position plus some constant, well, not constant vector, plus some vector b, which is dependent on time maybe. Most of the examples we'll look at in this course is where we just have a constant matrix A multiplied by x, and sometimes we have the inhomogeneous b of t. Right? So in this simple type case, we know that it is linear, which is quite nice, meaning it has we can split it up with addition and multiplication. So the solution space is also a vector space, which is quite nice for us. So we can do the same thing of the general solution of the homogeneous is linear combinations of linearly independent solutions. I should say that homogeneous equation is where we have node B. That one's a vector space, whereas we have B, we just find one particular solution, and the difference between solutions would be a solution to the homogeneous. Okay. All right. So yeah. So applying that kind of theorem involving Lipschitz constants before, we have this theorem here regarding existence and uniqueness of solutions to this first order dynamical system now, the first order differential equation, that if A and B are continuous, and that's including the case where A is just a constant matrix, then what we would get, and also B being continuous is pretty much in every example we're ever given, then this equation has a unique solution specifically for this kind of bounded time interval, okay, which is quite nice for us. So that's very nice. And so working forward now, let's talk about what the solution would be. So let's look at the simple case first. We talked about where we have the derivative vector is equal to some matrix multiplied by x. Then in the simple case where we have unique eigenvalues with their respective eigenvectors Vj for our matrix A, then it turns out that we can write the general solution as a linear combination of these eigenvectors Vj multiplied by e to the lambda j times t. Okay, so quite nicely like that. Okay, so some linear combination of them. Okay, so it kind of mimics the same idea where we have, say, dy by dt is equal to a times y, where the solution would be some constant a times e to the at, right? So it's the same kind of idea here, right? So it works out quite nicely in that regard with the eigenvalues. So looking at the eigenstuff of matrices is quite important. And so working forward a bit more generally is what we can say if we kind of have defective matrices which don't have all unique eigenvalues, or we have to do a bit more work in some cases. What we can say is that if we have this type of equation again, which we looked at on the previous slide with initial condition, then it turns out we can write the exact solution in this form using what we define as the matrix exponential. So if you kind of think about it, it doesn't really make too much sense to raise e to the power of a matrix. But what we can do is using the same Taylor series of just the regular exponential. So you remember from Math 1b, exponential is this Taylor series. You expand it all out, x to the k over k factorial. And so if we replace that with a here, plug in a for that. So our identity matrix defined in like a to the naught is I plus a squared, then it turns out we could do it like this, and it works out actually quite nicely because you get kind of some of the same properties as you would get from applying this Taylor series, which we'll see on some of the next slides. And so this is also kind of mimicking that idea of this type of solution, this one here, to this case in R1, okay, whereas this is in Rn. Okay, so we're kind of replacing here this A with the matrix A. I should maybe say this would be like a constant, I should say, so you're not confused A with the matrix on the previous slide. Okay, so looking at the matrix exponential, what we first need to look at is this idea of diagonalization. So you may remember from Math 1b, we say that, or we rather know that a matrix is diagonalizable. Right, so we define a matrix as diagonalizable if there exists a invertible matrix, a non-singular matrix Q, such that we can write A as Q times this gamma, this gamma here, right, drawing my gammas, times Q inverse, right? Where gamma is a diagonal matrix. Specifically, the theory tells us that gamma has to have the eigenvalues within it, and Q has to have the eigenvectors in it. And so that means that such a Q only exists if we have a basis of eigenvectors, which isn't always the case. So there are cases where we don't have a basis, but if we do, then it turns out, and we can write A as Q times gamma times Q inverse, then we'll see in the next slide that this lets us find the exponential quite easily. Because what we can do is similar to like raising a matrix like this to some power, we can say that the exponential of A is Q times the exponential of the diagonal matrix times Q inverse, and taking the exponential of the diagonal matrix, what you just do is just kind of do the exponential component-wise to each of the values in it, which works out quite nicely. So we have e to the lambda 1, dot, 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 e to the lambda n. So it works out, it's very clean in this way. So if you have a diagonal matrix, what you can do, find the eigenvalues, diagonalize it, and then raise all those to the exponential. And then once you do that, you multiply it again by Q and Q inverse, and you get your exponential matrix so that you can write your solution as y equals to y naught e to the, I shouldn't write it like this, it should be the other way around, e to the at times y naught. Okay, so that's your general solution to your differential equation, that being the 1 dy by dt is equal to a times y. Okay. All right, so there's a bit more work to be done in the cases where we're not diagonalizable, but for now, applying this to the inhomogeneous case where we have a constant matrix and a function b, or f in this case on the other side, we have this variation of parameters formula, which you've hopefully used a lot, particularly in class test 2, which allows us to solve the system by slapping in, what we do here is use that kind of same idea of the integration factor, pretty much. So you can kind of revise how that works, but this is what the formula is. I don't think it's particularly hard to remember or particularly hard to derive, so maybe look through the lecture slides if you're not entirely familiar with it, and hopefully also maybe review some class test 2 or final exam questions if you want to look at some examples of using it. So now to kind of work in the case where we might not necessarily have a diagonal matrix, we first need to define what's called a fundamental matrix. So a fundamental matrix, what we would say is a matrix is fundamental. Sorry, we have a fundamental matrix in respect to this differential equation, which is the one we've been trying to solve on previous slides, we say that we have a fundamental matrix phi if it satisfies two criteria. First of all, it kind of satisfies the matrix version of this equation. So instead of x dash and x, we replace it with phi dash and phi. So it's now a matrix equation instead of a vector equation. And also, phi is invertible, meaning that it has linearly independent columns, because we want phi to kind of represent what we're going to say now, which is phi represents a basis of solutions to this differential equation. So that's quite nice. So if we have like the general solution to the differential equation, we can slap those in phi, and that would be a fundamental matrix. Okay? And it turns out that any solution to a differential equation would just be any fundamental matrix multiplied by some constant vector that depends on our initial conditions. Specifically, if we have the initial condition x naught is equal to say x naught, then we need that to be equal to phi naught times c. So this c, since we know that phi is invertible, would be phi inverse of 0 times x naught, which is quite nice. So we can put that in here. And that means that we would have to have, this is our solution here, but we also know from before that the exponential matrix is also a solution. And we know because of uniqueness of solutions, these two have to be the same solution, which means that this phi of t times phi inverse of 0 has to be equal to the exponential matrix. Right? And this is the key equation we need here that says if we're trying to find the exponential matrix and for some whatever reason we already have the fundamental matrix, then all we have to do is multiply by phi inverse at 0 to get the exponential. And this is an example of that. What we can say here is first we want to find a fundamental matrix, then we want to find the exponential of A. So first of all, looking at the eigenstuff of A, we can look at this. So lambda plus 1 squared minus 1 is equal to 0. So lambda squared plus 2 lambda is equal to 0. Okay, so lambda equals to 0 or -2. Those are our eigenvalues. So our general solution would be, by inspection, the eigenvector for the eigenvalue 0 would be 1, 1. So 1, 1, find some constant. And then for -2, it would be -1 plus 1, 1, 1, -1 plus 1, 0, 1, 1, 0. So in this case, 1, 1, 1. For the null space, we need. Actually, did I do that right? Need 2. Oh, yeah, plus 2 jokes. So this would be 1, 1. Okay, so we need 1, -1. Okay, so this is what it will be plus c2 e to the -2 t times 1, -1. So our fundamental matrix phi could be 1, 1, because we're just slapping in linearly independent solutions, e to the -2t, -1, like this. This should also be t. Oh, that's not a t, that's just a 1. E to the -2t. So phi of 0 is equal to 1, 1, 1, -1. So e to the at is equal to 1, 1, e to the -2t, negative e to the -2t, times the inverse of this matrix. So just put that maybe down here, times, matrix at 0, 1, -1, inverse. So we were looking at 1, 1, e to the 2, -2t, 2t times, it was 1 over -1 minus 1 times leave 1, 1, leave 1, leave 1. That's our inverse. So multiplying these two together, you would get your exponential matrix. So I'll leave it there for you guys to do the rest of the calculations. But hopefully you see the pattern here. Okay. All right, so that seems pretty good there. Oh, didn't mean to jump too far. All right, so some quick little theorems about commuting matrices and nilpotent matrices in regards to the exponential. First of all, well, by definition, a matrix is nilpotent if there exists a integer k such that a to the power of k is equal to the zero matrix, the zero matrix being 0, 0, 0, zeros all everywhere. So that means if we kind of think about the Taylor series plugging in the matrix A into that with our exponential, what happens is that if, well, here we're saying that k is equal to k0 plus 1, then if we have a nilpotent matrix of kind of order k0 plus 1, then we only have to look at the first k0 plus 1 terms, as in the identity up until k0, because otherwise everything would be 0. So 0 matrices plus here, which you don't really want to care about. So this is what we would say the exponential matrix would be in this case. So that's quite nice. I think we have an example on the next slide as well for that. But here as well, we also have a theorem that says if we have two commuting matrices, A and B, then what we can say is that we can use that kind of index law where we're saying that e to the b plus c is the product of e to the b, e to the c, which is quite nice. So it respects that index law in that case, where specifically b and c commute, which has been meaning to say bc equals to cb, which is not always true though, just so keep that in mind. Yeah, and so if for some reason e to the b and e to the c are more easy to compute than e to the a itself, then that's what we want to use here. All right, so you can use that if you want. So let's look at this example here. So we want to use that idea of having a nilpotent matrix and finding the matrix exponential. So let's find a to some powers to see that it does eventually give the zero matrix. So a squared will be this multiplied by itself. 1, 1, 1. It's equal to 2, 0, 2. This would be zeros. And this one would be, did this before, then no. This would be 0. Is that right? This one would be, yeah, this one would be 1. This one would be 1 as well. Negative 1, negative 1. Yeah. Okay, and you can convince yourself that then from there that a cubed would be equal to 0, the zero matrix that is. Okay, so didn't need to do that. Sorry, this is just a bit finicky. So what that would mean is that e to the at in this case would be equal to the identity plus a squared or over 2 plus just the zero matrix, because the Taylor series would just be 0 terms up beyond that point. Or I should have t and t squared here. Yeah, t and t squared, because you need to remember to put in your t into your Taylor series in a way. So this is equal to 1, 0, 0 plus t times 1, 1, 1, 1, 0, 1 plus t squared over 2 times that 1, 1, 0, 0, negative 1, 0, negative 1. So if you expand all that out, what you would get is that exponential matrix that we want, okay? So that's all we need to do in this case. So hopefully you can verify those calculations there. I don't see really a point of expanding on that now. Okay, let's move on. Okay, so in terms of now equilibrium points, that's kind of the last, well, one of the last things we'll be looking at here. We say that position vector A is an equilibrium point of our kind of matrix equation, not our matrix equation, but our dynamical system, if it means that our velocity at that point is the 0. So we're not going to move anywhere at that point. And so that means we're not going to go anywhere, meaning that the solution to the differential equation at with initial condition A being that same equilibrium point position means we're not going to go anywhere, meaning the solution is just we're staying at A. Okay, so that means that we have this at least here, this at least equilibrium where we're saying if we start at A, we're not leaving A. And now what we're going to be interested in is the kind of long-term behavior of if we start near A, do we either stay near A always? That's what we call stable. Or if when we start near A, would we eventually approach A as we go to infinity? In terms of time, that would be asymptotically stable, or do we diverge from A, which is unstable? Okay, so that's what we care about when we're talking about an equilibrium point of our vector field, where we have the vector field function f evaluated at A being 0. Okay, so let's define those ideas of stability, instability, and asymptotically stable a bit more. So you can look at the intuitive idea here. Hopefully you have that established already. But kind of the precise definition is that if we have our initial condition close enough by this norm of our vector, it's quantified by this delta, we're saying that if we're given some epsilon, we're saying that this delta always exists such that if we start close enough to A in terms of delta, then the solution to a differential equation will also always stay close enough to A in terms of epsilon, okay? So that's quite nice. That's something that we want because we want to look at the long-term behavior of our, because we're saying this applies for all t, like arbitrarily large t. So we're saying that it works out nicely in the long-term run of our solution to our differential equation. Okay, and then we have this idea of asymptotically stable, which is where we kind of get a bit more in this definition, which is when we're saying that in the specific subset D, which in R2 would pretty much be a domain because we're saying that it's an open subset, then we say that the equilibrium point is asymptotically stable if it is, well, first of all, already stable, and it is such that for all initial data x0 in our domain of attraction D, then the solution to the differential equation starting at x0, this dynamical system here that we've been talking about thus far, would approach A as t approaches infinity. So we get arbitrarily close to that equilibrium point, as in we're effectively just going to stay near the equilibrium point as t gets arbitrarily large, right? Okay, so we kind of get sucked into the equilibrium point. Well, we should quantify a bit more because we'll look at some examples of what it means to get sucked into the equilibrium point in a few the next slides, but that's enough for now. And then in terms of determining whether or not we have stable or unstable or asymptotically stable, we have this nice theorem which says if we look at the eigenvalues of our matrix A, then we are stable if and only if the real part is less than or equal to 0, meaning that kind of by what we looked at before, the linear combination of the C e to the lambda t times vector, well, that's in the simple case where we have enough eigenvalues, but it turns out this also works in the this intuition establishes it for the case where we have distinct eigenvalues, but this theorem works even if there are distinct eigenvalues. But here the intuition is that lambda are all not positive, then as t approaches infinity, this term would either become constant if it was lambda was 0, or it would approach 0. Okay, and it turns out when the real part of all our lambdas are negative, then all these terms would approach 0, which is quite nice for us as well. Okay, so those are the two criteria for stability and asymptotically stability. They're if and only ifs, meaning that all the other cases where we have, well, if we have at least one real part of our eigenvalue be positive, then we are not going to be stable at all. Okay, so moving on. So we can also look at what the complex case is for solutions, because we looked at on the previous slide the real part of our lambda rise. So we now need to talk about um, what it means to kind of look at the real part of everything, kind of what the intuition behind that is. And it's really the same as doing them with a complex case of, say, roots of the Ingersoll equation or a characteristic equation in topic 1. So here what we're talking about is if we have a matrix A with eigenvalues that come in, well, if we're working with matrix A, we have to have eigenvalues that come in conjugate pairs. Then we also have to have eigenvectors in conjugate pairs. You can hopefully think about why that is. And so what we can do is kind of, if we look at the e to the lambda times our eigenvector, if we expand all that out, we get one real part and one imaginary part from that by expanding out this multiplied by the simplified like e to the alpha t times cosine beta, cosine plus I sine beta. So we get the real and the imaginary part. And so that's what we can use to form a basis of our solution space. Right? And then really the kind of the important thing to look at here is that we get the e to the alpha t multiplied by these kind of stable sign terms, meaning that it's in the long-term behavior, the alpha that matters. So if alpha is negative, then this alpha e to the alpha t factor approaches 0. So the whole thing approaches 0, the 0 vector that is. Otherwise, if alpha is 0, then it just stays kind of oscillating back and forth with the sine and cosine and sine. Otherwise, the final case is when alpha is positive, in which it diverges, it gets arbitrarily large. Okay, so that's kind of the intuition we're dealing with there. So now we're just looking at a few different cases and some nicely drawn out diagrams for those. So first of all is the case where we have, well, we're going to be looking at cases dealing with R2, so 2 dimensions, because that's the only real case you have to look at in the exam. These examples on the coming up slides, they're not exhaustive, so they don't cover all of our cases, but I believe they should be enough for the test that we want to look at. Otherwise, you can look at some other past paper questions. Here's the case where we have two negative eigenvalues. In this case, we can write, for instance, the general solution is something like this, right? So what that would look like if we draw a phase diagram. When we want to draw our phase diagram, first thing we want to do is draw our eigendirection. So if say 1, 1, that's roughly this direction. And we also want to look at how, since it has a negative eigenvalue, we're saying it's going to, near that direction, we're going to attract solutions towards the center, because our equilibrium point would be, because this is for the system, x dash is equal to ax, where a is a matrix, not to be confused with this, which is just some constant. So it's going to be attracted towards the center because 0 is our equilibrium point. And the same is going to happen here because we have two negative eigenvalues with this other one, which is, oh, sorry, I did it the other way around. Oh, no, that's right. Yeah, this one would be the 2, 1 direction. This would be the 1, 1 direction. Then it also attracts inwards, right? And so that means that solutions would kind of be affected by both of those as they go along. So what you can say, for instance, is that as t gets arbitrarily large, this term becomes smaller much, much faster than this term. So this one would have a stronger effect, as in it will be more present as time gets larger. And you can kind of see how that is, where this example trajectory flows this kind of direction, where it gets a bit more close to, yeah, it's a bit complicated to kind of draw it like that because this isn't the very nicest case, but you can kind of see how this one would be the dominating term as t approaches infinity. But there's a few more nice examples, and the ones you get in your exam would probably be a bit more nice than this one. So this one now is kind of representing the case where we have two distinct positive eigenvalues. So that case, we can do the same thing. We can draw eigendirection. So 1, 2, that would be this direction here. So that's the kind of weaker eigenvalue. So you can kind of see for the stronger eigenvalue, the 1, 0, this direction here, you can see how the solutions kind of asymptotically approach this direction, these solutions here. The reason being is because this e to the 2t, which comes from the solution in this case, dominates as t approaches infinity, kind of similar to what we talked about before. So this is the one that affects the solutions more, so it approaches that direction no matter where it starts. For instance, if we were to start here, it approaches like that. So it approaches that dominating eigendirection as t approaches infinity. Okay. Yeah, so it may start close to V1, but approaches V2 closely. Okay, so you want, when you're drawing your phase diagrams, just draw in the, and I remember Chris also made a good video on phase diagrams that you might want to also review. Make sure you draw your eigendirections and then some example trajectories. For instance, going back here, so another example trajectory, as we kind of discussed how, some other example trajectories could be the one in here going towards the center, which would, as you can kind of see, it gets closer to this direction because this one, as we discussed, and same with this one, I'm now realizing, it gets closer to this direction because this curve becomes smaller, faster. So it approaches the direction like that. Okay, so that's kind of the intuition. You might want to have a look at that again. All right, so the next case is where we have the same eigenvalues, where we have a kind of matrix of full rank, meaning that all vectors in R2 are eigenvectors, meaning that every direction, all that happens when you multiply by your matrix, it gets either stretched out if the eigenvalues are positive or contracted inwards if the eigenvalues are negative. So we can draw our eigendirections, and what you could really say is that any trajectory would just go along a straight line. It'll either go inwards if the eigenvalues are positive, outwards if the eigenvalues are positive, inwards if they're negative. All right, so either attraction or repulsion. And then this case here, kind of one of the more interesting ones, is where we have one eigenvalue positive, the other negative. So say the positive one is in this 1, 2 direction, that's up here. So we'd be going upwards on these two, whereas we'd be going on the other eigendirection we have in this example, we'd be going outwards. This one should be inwards. The negative one would be going inwards. Positive one would be going outwards, right? So we have, say, a trajectory like this, right? We're approaching the positive one because this term, the negative eigenvalue, kind of linear combination of solutions, that goes to 0, and then this one dominates or approaching this direction no matter where we're starting. Okay. So draw your trajectories for these types of questions, and in this case, you want to eventually point towards the direction corresponding to the large second eigendirection. Okay. So hopefully you guys can see the pattern we're kind of developing here. Last thing we want to look at is the case these two of foci and centers where we have complex eigenvalues. So in this case, we have some sort of rotation. In the first case where lambda 1 and lambda 2 are purely imaginary, that's when we said we have stability, but not asymptotically stable. So that means we just have kind of our solutions is just some types of cosines and sines, and so we're rotating about rotating as some sort of ellipse like this. Okay, and you can work out, like using the techniques on the slide before, specifically what that would be algebraically represented as, but it looks something like this with these two types of ellipses here. Some different examples, depending on our starting point, of course. Okay. Finally, the one perhaps a bit more interesting is when we have this alpha in our solution, where we have two eigenvalues that are conjugates of each other. That's when we have like the e to the alpha t times like your sine, cosine, and so forth, dot, dot, dot. If you like your p and your q, the precise form was on the previous slide, but this part is just going to be kind of stable, so it's just going to be circulating, whereas this kind of radius here is getting larger and larger, or smaller and smaller, depending on whether alpha is negative. If it's negative, then we're going to be spiraling inwards because we're going to get contracting in towards the center, the foci I should say. Whereas if it's positive, then we're going to be spiraling outwards, right? So this is kind of consistent with that idea of asymptotically stable, and so forth. And so hopefully you guys can see that. So that's the kind of last case we're looking at here. If you want some more cases, you can review some examples that Chris has given. All right, so 2 things to just wrap this up now. First of all, we're looking at this idea of first integral. So this hasn't really been examined yet, but it's hopefully not too difficult. It's what you can do when you're given a differential equation to kind of look at a quantity that would be constant. Usually that quantity is either given to you or it's pretty easy to work out by kind of playing around with a few things. So what we call a first integral is a function g, that is such that if we plug in any trajectory, it's always going to stay independent of time, as in g is not going to change with respect to t. So an example in kind of a physical context is, say, the total energy of a system. So say if you're looking at kinetic energy in the case of a spring plus the spring's potential energy, that would be half mv squared plus half kx squared. That's constant. There's some constant, and that's just a combination of v and x, right? So that's not explicitly dependent, doesn't explicitly have t inside of it either. Okay, so that's really what we want g is, because in this case you're mapping from v to x to some constant. So we're saying that the trajectories in this type of example is some sort of ellipse. Okay, so it gives a geometric interpretation of what we're looking at, specifically algebraically a bit more. You could say, say in the R2 case, then if you look at nabla of g, which is just say the derivative of g with respect to x, derivative of g with respect to y, in the case of R2, then it turns out that that's always going to be perpendicular to this f. So remember, f was the change in x over change in t, in this case change in y and change in t. So if you dot product this out, you can kind of see how this resembles the chain rule. So we're saying the total change in g, by looking at like each different component, x, and then relating that to t, that doesn't change at all, okay? So that's how you can play with it, okay? So that's pretty nice like that as well. Okay, right, so that seems very good. Yeah, so we're saying that g is kind of a level curve of f, as in it's not going to change. Or maybe I don't have the best interpretation there. Because, yeah, if you might remember from 2111, nabla of g is perpendicular to where g is constant, kind of level curves of g. So we're saying that, yeah, this nabla is perpendicular to our velocity. Yeah, so the velocity is going along that place where g is constant, if that kind of makes any sense. You might want to revise that from 2221, oh, sorry, 2111, don't revise 2221 because that's what we're doing right now. But yeah, that's how you can interpret it. But like, we'll just look at here. So with this example, with v, we can look at, just doing it kind of algebraically, you can look at what kind of dv by dt pretty much. That would be partial v of a partial x times dx by dt plus partial v of a partial y times dy by dt. This would be maybe 2x, and then dx by dt, dy by dt is equal to yx. So this would be times y. This would be 2y times x. So this is equal to 0, as we want. So that means that v is always going to be constant with respect to time. And that means that our trajectories would look something like y squared minus x squared is equal to some constant. So what those look like in our phase diagrams would be parabolas. Okay, so some maybe like that, like maybe like these two or these two, depending on, yeah, I kind of messed up the diagram, but that doesn't matter. So it's something in our phase space that looks like a parabola, okay, would be what our solutions would be like, okay. So now we'll look at the last thing, just real briefly, which is Putzer's algorithm. First of all, we need kind of the setup as to why it works. So you may remember what we talked about with the characteristic polynomial of a matrix. That's when we plug in lambda I minus a as our matrix, and we look at the determinant of that. It turns out if we look at that polynomial, and instead of applying, say, this lambda to it as our independent, if we apply our matrix A to it, then that yields a root. So the matrix A satisfies its own characteristic equation, which is quite nice, and that makes Putz's algorithm work here. So Putz's algorithm says that we can find, in the cases where we might have defective eigenvalues and so forth, or a defective matrix, we can find the matrix exponential by applying this algorithm, where we have these polynomials p, well not polynomials, but these functions p, that we'll define on the next slide, multiplied by some matrix m, where mk is kind of multiplying, kind of sort of emulating the roots of the characteristic polynomial up to a certain lambda. We're multiplying a minus lambda I up until a certain point if we enumerate our eigenvalues in this kind of way. We'll look at an example in a few slides. So this is kind of what we can look at with this is the definition here of our vector p, so the p1 through pn that we're using, where we're saying that p dash of t is these lambdas along the diagonal in that specific order with ones below it, and it has to satisfy this initial condition of 1, 0, ... Okay. All right. So in the n equals to 2 case, what hopefully you've seen before is that we do this, and it turns out that the initial condition will be p of 0 would be equal to 1, 0. Yeah, 1, 0. Whereas here in the n equals 3 case, it'll be 1, 0, 0. Okay. And we have these n matrices like this. Okay. All right. So I think I'll just briefly walk through now. Hopefully, if you just have a quick look at this here, this makes sense. We're saying lambda 1, lambda 2, multiplying this is our m, this is our p's, and this is the kind of, in this case, p. Yeah, we'll look through an example of n equals 3 now. So just writing out there. So for this matrix, hopefully you can verify that our eigenvalues are lambda equals 1 and negative 1. And we can, 1 would have multiplicity 2, you can also verify. Negative 1 would have multiplicity 1. The question would typically give that to you. Let's find what e to the at is. So e to the at would be identity matrix times p1 plus a minus lambda. A minus identity times p2 plus a minus identity squared times p3. All right, and we need p1, p2, p3. We call that p. We need p dash is equal to, go over here. All right, we need p dash to be equal to 1, 1, 1, 1, negative 1, 1, 0, 0, 0, 0, p, and p naught to be equal to 1, 0, 0. So you can verify if you want that. That would mean that p would be equal to, this first one would be e to the t, and this one would be t e to the t. You can verify that if you want. And then for p3, we need p3 dash, kind of writing out this equation. We need that to be equal to p2 minus p3. So the homogeneous p3, so u homogeneous of this differential equation here would be e to the t, and the inhomogeneous would look something like, because p2 is equal to t e to the, so this would be negative. Yeah, this would be negative. No, wait, that wouldn't be negative. This one would be negative. This one would be negative. Something like t e to the, t e to the t, but multiplied by some constant, and then you can use, we also need, because it has a t here, plus b times e to the t. Okay, and then you can use that method we spoke about before, where you substitute that in to find what a and b would be. You could do that if you want to. Kind of, this is just applying it out here. In the interest of time, I'll just say that, well, to find a minus I, this would be 0, 0, negative 2, 2, 1, 1, 0, 0, and then a minus I squared would be equal to 0, 0, 2, 0, 0, negative 2, 0, 0, 4. Because I'm not having the best space to write this out here, you can follow up with the rest of the details. But this is kind of the groundwork of all you need to do. I believe the rest of the solutions are written out nicely in the slides, and you can also, as an exercise, try this out in this second case here. But in the interest of time, I do have to head off now. Okay, so you can try it out for this example here, and for this one down the bottom. I do remember, I think, what the answer for this one should be. So I just need to scroll down a bit. This example should have e to the a is equal to 1 e to the 2t, t e to the 2t, e to the 2, and you may remember that if you've done 2, 6, or 1. Okay, so that's what we want to look at in that case. All right, so apologies for kind of the interruptions here, but this is just some surface level things, and you want to look at the precise details in the slides would be a bit better here, but hopefully you kind of see what I was kind of sketching a bit of a solution to. So I just have to wait for Thomas to get back, and he'll run you guys through the rest of this. Yeah, Thomas is here right now. So other than that, I'd say definitely remember Putz's algorithm and the kind of formulas involved in it, because you won't be given a formula sheet in the final exam to remember what Putz's algorithm is, or the kind of definitions of those p vectors, or the matrices M that you need. But you won't have to remember things like the variation of constants, variation of parameters formula, because that will be given on the formula sheet in the exam. So I think this is sufficient for what you need to practice for topic 2, just anything you're confused on by what I briefly walked through. Okay, so now the kind of more important part that hasn't been examined yet, Thomas will now run you guys through, which is topic 3 and topic 4. So best of luck with the exams, guys. Sorry about kind of the technical difficulties and me rushing a little bit. Hopefully you guys enjoyed. Okay.
Right. Stream. Okay, we should be good. Okay. This is working. Alright. Yeah, I think this is working. Good. Alright, so yeah, so we're just gonna be like going through like part two. Basically just like the topics that Chris hasn't like assessed up to now. Now's like the part where I actually learn this for the final. So topic three, those are just like boundaries problems because in topic like one, yeah, just like topic one basically, you've been dealing with like initial value problems. So being given like some initial condition. So you might be given you might be given like t of 0 is like some like random vector. The point is that it's initial state, so it's like always limited to 0. But however, now you can be given say multiple sort of data points. So you might be like t0 is something like t of pi is something. So you can get all sorts of data points like in different boundaries essentially. So I'm mainly going to be doing like 1D, so it's mostly just triple to 1 to my knowledge. And then topic 4 is going to be generalized Fourier series. So topic 3. So we're going to have to define a bunch of definitions first. So the first thing we're going to define is the inner product. So the inner product is the generalization of the dot product. Instead, specifically for functions, the inner product between two functions is just going to be the integral of their product of the functions with like some like interval that we're going to define. So just a or b. And similar to like the dot product, when the dot product was like 0, we call them perpendicular, like orthogonal. It's a similar notion here, where if the dot product here is 0, we're going to call the two functions orthogonal. Again, over like the specifying interval that we're defining over. So once again, how we sort of define the length of a vector was like if we get like 2, 2, how we defined its length was we dot the vector with itself. So like something like this, and then we square root the resulting like dot product with itself. So the length would be like 2 root 2. Here for the norm of a function or like the length, it's again like the same thing where we just take its dot product with itself and then we just square root it. So obviously it would just be like the integral of the function basically just like squared. So the significance of this is that the integral of like a positive function is always going to be positive. It can't be negative because like there's no negative area. So this integral is guaranteed to be positive. Obviously, when you square root it, then it's still going to be positive. So it still like aligns with our notion of still having like a positive like I guess length. So consider these two functions. So find the inner product of f and g, and the norm of f. So here it's pretty self-explanatory. We're just going to chuck the over 0 and pi. So the inner product f and g is just be the integral from 0 to pi of the product of the two functions, so sin x and cos x. So it just reduces down to a simple integral. So we can take out like a 2 and like have like a sine 2x there and just integrate. So it's kind of easy. So g is equal to 0. So remember that when the significance of this again is if the inner product between two functions is 0, then the two functions are orthogonal. And similarly here again, how we're going to define the norm of the function is we're going to take the square root of the integral of the square of the function. So once again, just come down to like simplifying this integral. So we can use like a trig identity for sine squared. It's like 1 minus cos 2x on 2. So just like integrate each of these. So that's like x on 2. And then this one, that is half sine 2x. So when we chuck in if we chuck in 0, like 0 anyway, but if we chuck in a pi, this will go to 0, but this will go to pi. So the inside will just be pi on 2. So when you take the square root of that, well, it's going to be square root of pi on 2. So that's the norm of f in this function over these boundaries. Okay, so once again, like the idea of like dot product is, I believe it's something like if you have the dot product of the absolute value of the dot product, it's bounded by the norm of like the two functions like that. So it's kind of like the inequality we might have seen like high school or something for like dot product. But again, like for inner product, it's going to be the same thing because like dot product is just inner product essentially. So this is called the Cauchy-Schwarz inequality. So any like two continuous functions, find like the absolute value of the inner product of the functions is bounded by the product of their norms. And another like sort of like inequality we might like derive is the triangle inequality. So the sum of like two functions, the norm, is bounded by the individual sums of the norms. So like essentially these will prove to be kind of useful if, say, are you trying to like prove like some like integral of like f of x squared plus g of x squared, something like that. Like it might be hard to prove, like just might be like maybe like using calculus, but like by using this result, like it's a pretty like neat result. So, like I believe it's like square root f of x squared, like the integral of that plus like the integral of like that g squared kind of thing. So once again, like you just kind of like need to have these properties. So linear second order. So instead we say like IVP, that's like initial value problem, but we just say BVP. So for like boundary value problem. So usually it's going to be in the form of this, where like you usually have like the same sort of LU expression. This may or may not be homogeneous. Obviously, like you specify your boundary, and then you similar to like your initial value like problems. You instead of specifying maybe like just u of 0, just like at a single point, you specify like multiple boundary points. So here we have like 3, here are like 5, and in fact, we don't even just see like u of like just a single expression like this. We might have like a linear combination sort of thing going on. So we have like a u dash, with the may not be constant there, and there's also like another constant for a u as well. Specify conditions for u dash and u. So we need to, obviously, because it's a second linear order. So in general though, if we can express this in a more general way, so instead what we have is A2, so like all these A's, they're not constants. Like they can, but in general they're just functions. And here again, like this is F, so like in most cases it can be inhomogeneous. So this is gonna be like the boundary over which like we're integrating over, or like doing our LU over. So we have these conditions here. So in general, what we saw here is that we had a bunch of constants. Instead of like those specific constants, we're just gonna be more general. Replace with these constants. So we say like B1, 1, and here we say like B1, 0. So like I'm guessing like this 1 here is like representing like the first line, and it's like the index of like the position in the line. So that's gonna be like the general form, and then that's gonna be like some random number. So this is kind of similar to an LU form or expression, but for like a 1D sort of like a one order LU problem. So instead, what we're going to do is we're going to call these like a boundary operator essentially, because it's very similar to like an LU operator essentially. Yeah, so like obviously we have like another one's like 2. So these two are going to form our boundary operators. So just so we can like make the like the conversion in the math a little easier. So it's like another one. There's like theorems. What's theorem 1? Oh, that one, the Cauchy-Schwarz. Right. The homogeneous problem. So remember, homogeneous is the one where like f is 0. So you don't have the f there. You have like the forcing term. So f is 0, and then all these are 0. The alphas, like essentially like what you subject your boundary operators to be, they must all be equal to 0. So if the homogeneous problem only has a trivial solution, so that's like if you don't have like any like other like not obvious like solutions, like maybe like y sine x or like e to the x, something like that, then for your inhomogeneous problem, no matter what you pick for your f or your alphas, the problem will always have a unique solution. So that's the purpose of this theorem. So here we're going to analyze, does the following boundary value problem have a unique solution? So essentially what we can do is like try tackle the homogeneous problem when this sine x is 0. So what we have is like u dash plus u is equal to 0. So from what like Brennan probably discussed, you'll probably see that this like inside like equation is gonna be like r squared plus 1 is 0. So it's gonna be like complex. So like when you have the complex roots going on, you don't have e's going on. Instead, what you have is like sines and cosines. So the general solution is gonna be c1 sine x plus c2 cos x. So that's gonna be the solution for our homogeneous problem. But then obviously we need to like make sure we have the right bounds. So like subbing like the right boundary conditions. So when u's 0, then what we or like when x is 0, I mean. So we see is like sine 0. No, I'm just gonna write the result. So when x is 0, then like the sign will go away. But then cos 0, that'll be 1. So we're left with like c2. And what's that equal to? Well, here, it's apparently equal to 0. Similarly, we're going to sub in pi. So when you sub in pi for x for sine, again, that's going to be 0. But then c2, that will just be like negative c2. But like we already don't care about like what this is because like c2 is 0 anyway. So just from this, we kind of only can conclude that u is equal to c, or yeah, just like c1 sine x. Because there's no restriction on like c1. Because like it doesn't matter what c1 is, it just gets annihilated anyway according to these boundaries. So like any c is like arbitrary is fine. So like in this like maybe like sub problem, this would induce like infinite number of solutions. So there would be an infinite number of solutions, but let's see. Let's talk about yeah. I was kind of like talking about only the homogeneous problem, but actually for the boundary value problem, because if we like sub that in, Oh yeah, no, we're meant to be using this room in the sense that the homogeneous problem, it doesn't have the trivial solution, because like if it was the trivial solution, we can instantly straight away conclude like the inhomogeneous problem is unique. But in general, though, like you might be like thinking this is like okay, like if this then that, like the converse won't work. So essentially, like if this thing doesn't have the trivial solution, then the inhomogeneous doesn't have a unique solution. Like I think that's the converse, like the contrapositive, like the converse. Like you might be thinking that's not true, but it does happen in this case. Like both ways also work, which like we'll discuss later. So essentially, what it is this homogeneous problem. It doesn't have a trivial solution. It has an infinite number of solutions. So just from this theorem, we can conclude, hey, the inhomogeneous problem does not have a unique solution. There are an infinite number of solutions. So not trivial, therefore not unique for inhomo. So that's the purpose of this theorem, essentially. Okay. So now we're going to move on to adjoint operators. So again, just like for like some random like differential operator, just for like second orders, that is, we're going to define the formal adjoint. So it's sort of like this kind of L, like it's like a little dash thing, like star, sorry, and then a V. So you don't use U because it's like when you have like y equals f of x, and then you have like you're kind of defining the inverse. So like using like the output letter sort of thing. It's not exactly the inverse here, but that's kind of like the analogy I'm trying to make. Is like trying to use the output of the letter of the output sort of thing. So V as the output, we're going to define that as essentially what it is like you put instead of putting the dashes on the U's only, you put it in the like on the outside of A2 and B as well. So you put it like on both of those. Again, it's like the same thing here, except you put this like little minus thing. Obviously, like the A0, like that would like stay the same. So that's the form adjoint. And then what we're also going to define is the bilinear concomitant. So we're going to define that as it's like a function of like u and v. It's equal to u dash of a to v minus u of a to v and then like dash that, and then U A1V. So it's kind of like just like a little garbled here, but that's kind of like what we define the bilinear concomitant as. And so the Lagrange identity is essentially just going to be like the sum of like those two essentially, or except like not quite, because what we have here is like P of UV, but it's kind of like in like an integrated form, like when you start being bounds for integration. So in actual fact, like there is another like form for the Lagrange identity. There's like the diffed version. So like there's like a d on dx like OUV sort of thing. So something similar to that. So when you diff that, like the inner product would like turn into something else, and then these bounds would kind of go away. It would just purely be P of UV instead. So like that's like the diffed version of the Lagrange identity, but they are indeed the same. Okay, so let LU equal to like this, find the form of adjoint. So what you recall is like L star V is equal to, so we're gonna put like kind of like put brackets around like that. So essentially like this one didn't touch, and then this one just like turn into like a plus. That's essentially what we're gonna do. So like let's work through the algebra for this. So alter the sign. Let's put the U there. Okay. So if I diff that inner thing, that's like U plus XU dash. So diff it once. Sin X U, that's like cos X U plus sin X U dash. I'll leave that last term to the end. And if I diff that first term again, let me just check everything's working. Yeah, okay. So diffing that first one, so we use U dash, there's no like constant term in there or something. And there we have that X will go away. So it's like U dash plus X U double dash. So that's like the first term. And then we have cos X U plus, so like we're not really changing anything there. So summing these all up. Okay, for the double diffs, there's only one. It's like the X U there. Okay, so for the U dash, we have like 1 plus 1, so 2. 2 plus sin X, so that's going to be like our coefficient of the U dash. And then for the U, we just have cos X. And then, like I said, I've been saving that to the end. So just EX plus 1. So just like just punching for the math here, just a bunch of diffing. But that's kind of really it. Yeah, so at least I swapped it around, but yeah, it's the same thing. Right. So an operator is formally self-adjoint if the operator of like LU is the same thing as L star V. Like obviously, like if the letters were the same, then if if we somehow like got like LU is this, but then if we found that L star V was also like this exact thing, except we just like anytime you see a U replaced with a V, then it's gonna be called it's formally self-adjoint. So the other like sort of important theorem is an operator is formally self-adjoint if and only if it can be written in this sort of form. So it's very specific. So why should we care about like this form? It will be like explained later essentially. But like writing this one, like it basically allows like really good applications. So obviously again here like P and Q, they're just arbitrary functions. Okay. So any sort of ODE in this like sort of general form again, you might have like a forcing term. It can be transformed into self-adjoint form if you essentially like divide this expression by A2. So it kind of becomes U dash plus A1 on A2 plus A0 and then divide by A2 again. And divide that. So the reason we do this is we're trying to like sort of focus on this here. This is like kind of like okay, like we don't even want because we're trying to link it to this sort of form. Like how can we make it similar to this? This QU, like it's kind of like already in that form. We don't really do anything, but it's like we're trying to sort of compact this into a single sort of integral, not integral, like essentially like a diffed form. Like essentially what the spoiler here is essentially like a product rule. So it might be like maybe like we have like x squared y plus 2xy, but then like something like that. Then you recall like if we kind of want to compact that in like a single sort of like diff form, like the diff of like a product. That's essentially what I'm trying to say here. You want to express this as the diff of a single product, just similar to this as we saw like back in like topic 1. So how do we kind of express this in that kind of compact form? We're going to use an integrating factor here. So why do that? Because we can actually see. Okay, I'll just use this form like e. So like e that dx u double dash a1 a2 dx. Okay, but you just have to like times this thing to the others as well. Like I'm trying to focus on this. The reason we write it like this is because this thing, we can rewrite that as the product, as the diff of a product of essentially this. E1, E2, dash. Okay? So the reason we do this is because when we like evaluate the product out, I'm just going to diff this first. So when we diff this, like U dash will obviously be U double dash. So that's where we have that. And when we diff this thing here would like stay the same. But then what comes out like the result of like a chain rule is going to be like the diff of this, or just like literally this expression here, because anti and int under each other. So out comes the A1 and A2. So that's exactly the expression we get here. So that's the motivation for like sort of bringing back integrating factor here again, because we can like kind of express it out in this form. But once we express it in this form, then what we can see is that we can probably like we can probably get like a negative something there. Okay, like I'll literally just doing this example because there's like actual numbers here. So write this in formally self-adjoint form. So again, like the first thing we want to do is before finding integrating factor, just make it in like this form where you just divide everything by like the coefficient there. So like plus like the function whatever. So x squared equals fx squared. So integrating factor here, like it's kind of already there, but essentially what you want to do is like get like 1 on x, and then you divide it. Okay, so like essentially you can't do it before and after. Like it really doesn't matter. So like I'm just integrating 1 on x anyway. So like, it is just L on x. Well, I was meant to e it. So e that. So just x. So essentially what you need to do is like multiply this expression here by x. So kind of just went from dividing by x squared and then just times your x. So like essentially just dividing by x. Who cares? But like it's like fine, because what we see here again, we can sort of rewrite that point as this essentially. So we have that kind of form. So it's really close, like just a reminder, like LU is that thing. So it's really close because it's like the bracket like P like minus bracket P U dash and then like end bracket and then there's like a dash. I'm just gonna write it. Okay, so like P U dash and then dash again plus QU. It's really similar to this. Like this f of x, who cares? So this here is really similar to this. And then obviously this thing here is like, that's obviously in that form there, like use negative 2 on x. So it's really similar, but what we're missing is the minus sign. So, I mean, what we can do here is like pretty simple. Like we just like attach a negative to everything. So negative that, negative would be positive. And then like this again is like negative. So from this point, we're actually done. It's just a matter of like identifying what is what. So P here is going to be the thing in front of U. Oh, that should be dash. So it's just the thing in front of U. So it's just X. Q, that's going to be the thing in front of like this U. So it's like 2 on X. Yeah, like because we just have the forcing term. So I don't know what it meant to like. Maybe like R. So like R is the F on X. Oh, okay, like GR, like whatever. Like this is the kind of the result, like the self-adjoint form. Yeah. So now we actually like comes like the main point of the purpose of these writing this like really weird form. of a self-adjoint operator. So the point is any self-adjoint operator in that specific form, it will satisfy this identity. So it's like the difference of like these two specific inner products is equal to the sum. So like what are these terms here? So this B term, the B's should be recognizable because they're the result of like our boundary operators. So like nothing changes from like that. That's still the same thing. The thing that's new here though is this thing. You see like there's like a little R thing, like an R term. So what are these R terms? This R term, it's gonna be purely based on like the result, like the products of our like our P function multiplied by our U, like whatever the solution of your I'm assuming the homogeneous problem, and then you have to divide it by the coefficient of like whatever in our boundary operator was. And then there's also like another form. You can also express it as a minus of the same thing, but like the dash of like A, but then you divide by B of 1, 0. So it's kind of like you're linking these terms up. So it's like this and then this. So it's like it might be like a little confusing to maybe like remember. So you might be thinking like, oh, okay, like we got like two sort of algs here to represent this. Like, one is remember one. There are specific cases in which one might be like necessary than the other. So like the example I'll like go through next will showcase that example. So I'll bring it back. So it's kind of similar for like again like R2 as well. So right here is how we can determine. So it's kind of like what I was alluding back to, like if and only if like is the converse like true. Like in this case, yes, it's like it's called the Fredholm alternative. So here is like kind of like listing out like the necessary details here. These are like differential operator. So this is the same thing like that theorem. So if the homogeneous problem, there's only the trivial solution that works, then for the inhomogeneous problem, you're gonna have a unique solution for like whatever choice you have for like these specific parameters. If that is not the case, if you don't have the trivial solution, so you might have like an infinite number of solutions, something like that, then the inhomogeneous problem is gonna have a solution if and only if this specific sort of expression is satisfied. So the inner product of your forcing term along with your like V term, or like essentially one of your solutions is equal to essentially like these specific like linear combinations. So like that thing like from R, that's where that's going to come into play here. So these specific like linear combination for some reason. Okay. Yeah. So like pretty sure like this is like saying it's kind of like the superposition of your. Oh yeah. So V is the pretty sure V is the solution to your homogeneous problem, but then U is your solution to your inhomogeneous problem. So we can like times like a constant anything to V. That's fine because it's gonna be 0. But like you can't really do that for U because like you got this forced into like kind of deal with. Yeah. So we can use the Fredholm alternative to do this. So under what conditions will this specific problem have a solution? So once again, we're gonna kind of like consider the homogeneous problem, where again like U double dash was U is equal to 0. So remember like the solution for that was like C1 sine x plus C2 cos x. Here though we can't use the same like before though like 0 0. Here it's like any arbitrary alpha 1 alpha 2. So I mean it's still the same thing. Like okay, like how do we lock in the C like terms essentially? So let me just check here. Non-trivial. Oh yeah, okay. Well, kind of like saying like obviously our solution here it's not going to be trivial. Like it's kind of like similar to what I just did. So when you sub in 0, like C2, going to be equal to alpha 1. But then if you sub in pi, negative C of 2, it's equal to alpha 2. So what we can see there is alpha 1 is equal to like the minus of alpha 2. That's kind of interesting. Yeah, but like kind of like similar from before. Like, sorry, I did take it back then. the These would a on x. Like if you have like that arbitrary constant, because like it doesn't matter like what C1 is. Like it's just gonna get like negated by like the zeros and pi's anyway. So like that is our solution to our non-trivial. So it is a non-trivial solution. So like from here, like Fred Holm, you it's like mutually exclusive. Like you either go one or the other. So it's definitely not one. So we have to consider the second case. So what do we do in that case? We can transform into self-adjoint form first. So what we can do is u double dash plus u 0. We can put this. And then like typically we would need to do like some sort of like integrating factor or something like that here. Like if there was a u dash. We don't really need to do that. Like we can kind of just like maybe cheese it a bit. We say something like that. So like this is definitely the case. Like there's no need for product. We just like diff it on, just tag it on. So that is going to be our self-adjoint form here. So again, like when we have the self-adjoint form, I have to go here. Yeah. If that's the case, okay. Well, you can express this, or like you can go the other way. So you could also just express it like this if you want, because like these negatives, it's like linear, so it will still be positive anyway. So like I mean, like if you do this or this, like it should be fine anyway. I guess in this example, we just went through like have like big old positive, kind of like this sort of thing. So what do we do from here? That's when we're gonna use like this form here. So this one here. So I might need like constant look back, but we see like the R1 V that is equal to actually like firstly, let's have a look at this. Yeah, okay, I'm just gonna cover the formulas. It's like P of A V dash A over B1 0. Negative a bit. So we did have that other form, but I'll actually say this. So this is the time I'll say it. So we are not going to use that other form because there's a problem that we're going to get here. Firstly, we can identify like P that's equal to like just read off the coefficient. It's just like 1. Like normally it would be a function, but here it's just a constant. So it's just coincidence is like kind of like easy. So P is -1. Now the V though, so remember like our V, that was the solution to a homogeneous problem. So that V was equal to like sine. So like, let me just say sine x. So, and then A here, that's our, is it the result, should be the, like these ones, not the result of the boundary when you apply it. So A here, in this case, it's like 0. So, and then one more thing. Is B1 0? Yeah, B1 0 is like the coefficient for U, not U dash. Wait, what? Okay. So, like in this one, like it's gonna be this coefficient, so it's just 1. So here's the problem, because if we just sub it in, it's like P of A, like it doesn't matter because P is -1 anyway. Okay, but then if we sub in 0, what we're gonna find, if we sub in 0 for sine x, it's gonna be 0. So we're gonna get some sort of no, I meant the other one. So as in like this one here, because you notice that we didn't get any sort of coefficients for u dash. So these coefficients, like these ones here, automatically they become 0. So when you try to sub it in, you get sine because like that was the solution for a homogeneous one. That's like sine of 0. So already it's not a good look. You already have 0 on the top. But on B11, you also get 0 because we didn't get any coefficients for that. So you're basically getting like 0 on 0. So when an indeterminate form like shows up, it kind of sucks. So that's the case when, okay, like we can't use this form. We have to use another one. We have to use this other formula because like they're both equivalent, so it's fine. But we just have to resort to this one. So that's like why you might actually need like members like these 4 formulas. So yeah, like it is actually necessary. So if we are gonna like default to this one here, just can like calculate the diff and hope like it goes well. So for v dash, it's gonna be like the diff, so of sine, because that's a homogeneous one. So that's cos. So cos of 0 is 1. That'll be 1, 0, that's 1. So like this r term, r1 term, that's gonna be 1. And then similarly, we're gonna determine r2. Yeah, I was like scrolling ahead to like check what it is. Oh wait, sorry. Wait. The v here is like there's meant to be an a. So like it's just the arbitrary constant of a essentially. So it's a like that. Okay, so then for R2, again, what's the so P B V dash B B to 0. Okay, yeah. So once again, we're not gonna use the other formula because most likely it's gonna be like a 0 and 0 case. But then here, like we're gonna guarantee like it's not gonna be the case. So P of B, so that's like -1. And then here, V dash, it's gonna be A, so like cos, that's fine. But B, that's our other boundary. So it's from 0 to pi. So it's cos of pi. Still here, like the coefficient here, that's 1. So we're fine. Cos of pi, that's -1. So we just have A again. So we have these two terms for R1 and R2. So, okay, like now how can we put it all together? Remember that the inner product of f of v is equal to alpha 1 R1v plus alpha 2 R2v. So how can we calculate the inner product? Well, that's by using the definition. So literally, so our boundaries are just from 0 to pi of f of x. So v was our, again, a solution to the homogeneous problem. So a sine x. That's equal to alpha 1. And then R1v, so that's just a plus alpha 2a. So what we can notice from here is, like assuming a is in like 0 or something like that, we can just divide by a. So like this a is gone, these a's are also gone. So what we have remaining is just this. And that's essentially it. This is the condition that will guarantee if we're going to get a unique solution. So like if this, like whatever the forcing term is, essentially that must equal to, and times by sine x is equal to the sum of our like the result of like our boundaries, like alpha 1, alpha 2, like the sum of them essentially. So yeah, that's essentially what it is here. There is a solution if and only if like this condition is satisfied. So that's like the power of like Fredholm alternative and like kind of like the self-altering form, because like initially like when it's being shown to you, like it is really obscure, but like that is the application here of Fredholm alternative. Okay, so generalized Fourier series. Looking bored. Alright, generalized Fourier series. Okay. Yeah, it's like the bulk of this part, I guess. So first we're going to learn again is like this thing called weighted inner product. So you call like the inner product is like kind of like this essentially. But the idea for like weighted is like you're kind of like doing it on like a specific like scale kind of. So isn't it like when you have like the function for the like this arbitrary like weighted sort of function, you just tag on this weighted function inside the integral. That's basically it. Obviously, you're assuming the weighted function has to be 0. Yeah. And again, I guess like for the weighted norm, you are again kind of just like doing the dot product, not dot product, inner product, but then you're doing like if it was the normal like this inner product without the square root, it would just be like f of x, and then like w of x. It's like, I mean, this thing would be squared, but like the w of x isn't squared, it's just w of x on its own, and then you square that whole thing. So yeah, it's kind of obvious here. Again, here's saying like the several functions. It's like norm is like it's like it has to be less than infinity, kind of like infinity itself or something like that. So I thought I said this, but like two functions are orthogonal. Oh, okay, like under this like weighted function if again like it's equal to 0 or something. Yeah, maybe like don't assume w of x is 0 because like that would be kind of stupid. So then we have this idea of the orthogonality of a set. So if you have like a set of functions, they are the set is orthogonal. So if for all like if this goes up to maybe like maybe like fk because like there's n and m here, like just assume like n and m is distinct, so they can't be equal. Then you get any like sort of pair of two functions within the set. If they're orthogonal, then the inner product should be 0 essentially. Obviously, like not with itself because you're just asking for the square of the norm. So then there's idea of like how do you actually call what is a generalized Fourier series? So if we have this like random set that is orthogonal in like a random set of functions on the like boundary and then under like weights essentially, then if f is in the span of the set, so again like span is like the linear combination that makes f essentially, then we can define f as the sum of like some coefficient and then multiplied by each of our functions within the orthogonal set. And then we're going to define a of k as this. Now this form here is very reminiscent of something linear algebra. So it might have been like first year or something, like straight up high school. This here is very similar to like the Proj form. So like the Proj formula, if we're like kind of using the I guess linear algebra definition. Oh no, that's wrong. Wait. Flip. It's like A, and like A. So it's like this is like sort of like the scalar, like the scale how much you scale by sort of thing. And then like the vector you're projecting on, so A itself. So that is like okay, like if you really like care about like you can replace the I guess the brackets like the round brackets or something like that. Or like the dot product, I mean. So for the project like the vectors from like high school kind of thing. But this here, it's literally like the Proj formula. So, and then like here, like this kind of correlates to this correlates to that kind of thing. So I guess like the intuition is you're kind of just like saying like for each of these sort of for f like how much does each part within the orthogonal set like kind of contribute to f of x essentially? Like when you're asking like to project onto when you're projecting the function onto each of these sort of functions within the orthogonal set, and you're asking for like all the sum of them. Like the sum of them will kind of try to form this f of x essentially. That's kind of like what it's saying. So yeah, like the AK or like AI, whatever, it's the coefficient of like your Fourier series with respect to like your series here. Just know like n here that can be infinite, so you will see that like later. Okay, so given this like orthogonal set, find the series representation of f of x on f of x squared on negative pi to pi. So remember, like we're kind of just using that definition, like the one up there. Yeah, okay. Try to do it here. So, well, I didn't even rewrite it. Okay. So it's gonna be like the sum of all of these like terms. So let's just have a look at like A1, sorry. A1 of like phi of 1 of x. So like the first term, so literally just like this one here, like 1. So I mean, like the function itself 1, like it says a 1, but like how do we determine the coefficient? So again, that's kind of determined by this. So f, so like in this one's x squared of 1 with respect to like the weighted. Well, let me like if it's not stated, like we can just assume the weighting function is just 1. So like there's no weight. It's just the still like the standard. So 1 is okay. I have to like do this. So it's just like figuring out this coefficient. So in this case, like our bounds is negative pi to pi of x squared times by 1. So like doesn't really do anything. Okay, this is an even function, so let me do this. So this is like x cubed on 3, pi 0, like 2 pi cubed on 3. So that's the top expression. And then for the bottom expression, yeah, so like, I think I did this mistake sometimes, but when calculating this, like, I thought this was the absolute value, but yeah, just remember it's like the norm. So when you see like two lines, it's gonna be the norm. So it's gonna be the norm from negative pi to pi of 1 squared or just 1. So we just dx. So I mean, we just like pi minus pi. So it's literally just 2 pi. So what we have is 2 pi cubed on 3, but you divide that whole thing by 2 pi. So we just have this. 2's go away, and the pi reduces by 1. So we just have pi squared on 3. So that's going to be our first coefficient. Then we have to like deal with the others, which is essentially the different like ends of like cos x's essentially. So in general, we're dealing with like cos of n of x. So we have to find the, and obviously like whatever n is, like we just represent like our sigma sum essentially. So yeah, kind of like representing like the same thing here. It's going to be the inner product of x squared cos of n of x, and then divide by the norm of cos of nx. So this one here, we have to integrate again from negative pi to pi x squared of this time cos of nx. Okay, so once again, I'm just going to do my trick. 0 pi x squared cos of nx, because both of them are even, so it should be fine. Here, we have to do by parts. So put this one in like the d. In that case, you have to divide by n, and then like its sine. So it's like 2x squared sine of nx on n pi 0 minus 4 over n 0 to pi of, oh wait, no, you diff that. So it's like x, just like that. Alright, because I drag that 2 down when doing power rule. Okay, sine of nx. Let's see. So we're assuming here n is an integer because like that's like the pattern in our orthogonal set. When you sub in a pi here, like that's fine. But when you have sine n pi, when n is an integer, then sine of n pi will just be 0. So that pi will be 0. And then when you sub in 0, like okay, you sub in the x, will be 0. That's gone. So we just have like this thing to deal with. Once again, I'm going to do by parts again. So we're going to put the sine nx in the d. So it's like, when you put that in the d, it's like negative cos of n of x on n. So relating that to here, it's like we have 4 of x cos of nx. So when we have like the two negatives, they're just gone. Then we have the n here, but we also have the n from the when we put in the d. So that's going to be n squared. Again, like pi 0. And then I believe minus 4 over n squared 0 to pi of cos of nx. Okay, so this coefficient here, when we have cos of n pi, it doesn't go to 0. That belongs to sine, but it might be 1 or negative 1. So it depends on the nature of n. So like if it's odd or even. So that's way to think about this, like maybe like a graph. So kind of like this. Yeah, that's cos here. So the top here, like when cos 0 is like 1. When it goes to pi, it's negative 1. On 2 pi, it's 0. So when it's essentially even, it's 1. When it's odd, it's negative 1. So a way to represent that is with this, like negative 1 to the power of n divided by n squared. So that's what we can do to represent that. This one though, just ignore the 4n squared for now. Okay, like I'll just do it. Like essentially, again, if you just ignore this constant here, it's gonna be like sine of nx on n, like pi 0. When you sub in pi again, like, the result is the same, like 0. And then when you sub in like 0, that's gonna be 0. So like it does go to 0. Like I can't think of a way like think of the symmetry or something. with like the period or whatever. But the point is like that will just go to 0. We just have this part that's remaining. So that part survives. And then the next thing you want to do is calculate this. So the norm squared. So we found that the norm squared is, again, so we have negative pi to pi of cos of squared of nx. So 0 to pi cos squared nx. What we're going to do here is use a trig identity. Essentially this one. That's equal to 0 to pi. I believe it's 1 plus cos 2nx. So you double the... cos of 2nx. You have this. Yeah, just like integrate it. So like x plus sine 2 of nx over 2n by 0. When you sub in pi and 0 for like the sine, they go away. But like the sub into pi in the x though, that was stay put kind of. So it doesn't matter what n is, it was just equal to pi essentially. So now just completing the puzzle, what we have is that inner product, that first one, so that was like 4 pi of negative 1 to the n, divided n squared. And you have to divide that by the inner product of this, so pi. So yeah, I still want to clarify another point. Like, it just happens in this case, like, when calculating this, when calculating the norm, there's only like the projection sort of pseudo formula. So we like the square, so it's just the inner product of itself. But like, just remember in general, like when you're doing the inner product, to calculate the norm, like we'd have to square the, but here it's the square. So we don't need to do any square root shenanigans. Here the negatives, not the negative, the pi's will cancel. So we're just left with this. So that is going to be the coefficient of our, essentially like cosines, essentially. So what we have is like that first term, that was like, where is it? It's like pi squared on 3. So f of x, so that first term is pi squared on 3, plus, and then this is just for any arbitrary coefficient of the cosines, for whatever arbitrary n, essentially. So we have to say, we can say n, it's fine. And then that's our coefficient. So now our a of n is equal to that. Multiply by our orthogonal like functions essentially. So like in this case, it was like the cosines n's essentially. Cosines n of x's. In this case though, like it will just go to infinity because like in this one, it just like says dot dot. So like we assume it goes off. So like it just goes to infinity. So yeah, that's okay, yeah. Like essentially right here. That's how we represent our Fourier series for our f of x like in this domain here. Cool. Alright. So the next thing is this idea of completeness. So an orthogonal set is it's called complete if there are no non-trivial functions so that is like orthogonal to every function like s. Essentially, what that means is like if there's a function that is orthogonal to like one of our kind of like basis for orthogonal functions, then for like all of our orthogonal functions in like that set, we can conclude that the function itself that we're talking about must be like 0 essentially. So you can kind of think of it as like this set here. It's like it acts as a basis like for whatever like sort of space we're working on essentially. So here we can get a bunch of inequalities and identities, I guess, from like the Fourier coefficients kind of thing. So the coefficient, like the square of the coefficient, multiplied by the norm of the orthogonal functions, it's bounded by the norm squared of our function. That's Bessel's inequality. It's just bounded. But if we have a complete set, like essentially like I want to think about like if you have enough, maybe like if you have enough functions here, then they will essentially like if it's complete, then it's not going to be less than. It's actually going to be straight up equal to. So yeah. So if we have enough, if it's a complete set, then it was like straight up equal to the norm squared. I don't know if the fees have to be infinite in order to be complete. Put a question mark on that. But that's Parseval's identity. So here, we're going to use Parseval's identity to prove this here. So it's like this. The sum of the inverse is like 6. So it's like zeta is 6 essentially. So we have to prove this. Yeah. But we're essentially like given this sort of function to basically help us out. So yeah, I don't, because like this is like question I, so I don't think you need to have like prove that in the exam. Like maybe it is, but like in this case, like it's just like helping us out to basically just do this problem here. What we can do, like the original might be like something like this: x cubed is equal to pi squared x minus 12 blah blah, the same as so. So if we're asking about the Fourier series for x cubed, it is indeed equal to this. But you could just, as like kind of hinted in the this question already, the Fourier series of this is equal to like that massive sum there. So typically, like these kinds of questions, you want to form your Fourier series. So it's just the result of like your sum essentially, like this. Like you don't want to like obstruct of any other like terms like this or something. Just tag on the end. Just deal with that on its own. So in this kind of case, okay, so like again, like I think it's kind of implied that like we have like an infinite number of like functions to find out a formal set. So we'll probably just have to assume like if it forms a complete set. And when it forms a complete set, that's when we use Parseval's identity. So this one here. So essentially what we're recognizing is this here's our F. So that's our F. And then like each of these, technically like maybe like the 12 as well, chuck it in. That's going to be our coefficient. And then this here is going to be our function within our orthogonal set. So we just have like literally like listen to that definition there. Yes, it's kind of like what we stated here. So we're gonna have to ask for the norm of this squared, or literally just the the integral, negative pi to pi of pi squared x minus x cubed dx squared. So it's really just like a bunch of computation. Yes, we get that. I'm just gonna do my trick as usual, like take out a 2 for like because it's even, and then plan for x3 minus when you sub in 0 is 0, so that's fine. When you sub in the pi, so it's like 1 on 3 minus 2 on 5 plus, so like there should be like a pi to the 7 essentially. So like this is pi 7, that's pi 7, that's pi 7, so that's all good. So like that anything like gets like 8 pi to the 7 1 and 5, then he times out by 2, so it's gonna be 16 pi to the 7 and 1 and 5. So that is going to be our norm of our left side. And then what we have remains like we need to just tackle each of these. So our coefficient squared. So this is the time I actually do need like lob in the 12 there. So it's like essentially like the square of that. So if I square that, that will become 144. So the point like the -1 is it depends on if like n is even or odd or something like that. But if I square it, it's gonna be like positive anyway. So like that part goes away entirely. And that thing is equal to n to the power of 6. So it's on the bottom. So that's that. And we have this like final thing. So the norm squared of our sine of nx. So I might just go here. So negative pi to pi again, sine of nx squared. So just this. And then once again, just another trig identity. So I believe it's 0 to pi. Okay. 1 minus, I believe. So if the signs are different. Then we have this. It's like x minus sine 2nx on 2n pi 0. The signs will go away. It's like fine. But then what you have remaining is just the pi from the x. Yeah. So that is going to be the result of our like norm essentially. So kind of just compiling what we have. The left side is like 16 pi to the 7, 105. That's equal to, then, what is it? Okay, so we still have the sum though. Okay. Sigma sum n is equal to 1 infinity. So we conclude that anything for like the coefficient squared sort of thing. That was 144 on n to the 6 times that by pi. So that's really close to like what we're after now. What we're after is like one on, okay, it's like j by like n, who cares? So what we have is this. We just need to move this out of the way. So you just like divide that over because it gets sum, so it's fine. So 1 over n, that. So 16 pi to the 7, 105 times 144 pi is equal to, okay, calculate. Yeah, so like 195 expected. And then the pi here, that's going to drop down by 1, so 145. So that's how you use partial identity in this one. Kind of like, even though it's like an infinite sum, like it's still fine to do that. And we just like literally apply to like each like component. So like the key, like I guess like the start is like moving, like you might be given, like yeah, in that previous question, like something like that. There is like a similar question like do partial identity to find, I believe like zeta 4, so like powers of 4. So you don't want to do partials on this yet. Want to like I think you can, but like it would be easy if you just like deal with this infinite sum on its own. So essentially, you like want to move the pi square onto to the left. So just do the sum like on its own, because like it's literally in the form of like that essentially, or like yeah, this one partial. Yeah. All right. So yeah, it's the same thing. Okay, so some Louisville equations. So essentially, it's just this another like expression for an ODE, and it's specifically in this form. So it's really reminiscent of our self-adjoint formerly self-adjoint operator, which was like negative p of x, so u dash dash plus q of u. So it's kind of like if I like swap down the signs, this is 0. So it's really similar here. It's like I have like these exact things, except now I have like a lambda times r of x. So additionally, like also all this stuff is like just like zeros to make sure that you don't really break math or something like that. But whatever this lambda rx like rx is that's kind of inserted into here, we're gonna call that the eigenfunction. Because if I just move it to the other side, like that's fine. But if I move the other stuff to the other side, what I find is this plus q of u. Okay, like similar dx there. But that is our sort of operator for our self-adjoint form, kind of. So it's really similar to like I guess kind of eigen values like vectors, whatever, because it's kind of like you got this lambda that's kind of only like it's like a scalar of like the function itself, like r. So it's r is like our eigen instead of vector though, it's gonna be eigenfunction, and then lambda that's the eigenvalue. So once again, it's like how you might like refer to like linear algebra or something like that. Whatever eigenfunction is, it's gonna be like here, and then like our lambda that's gonna be an eigenvalue. So like we call that the eigenpair essentially. So here we have this ODE, and then we're going to transform this equation into Stern-Liouville form. So it's really just like honestly just asking convert this into like self-adjoint kind of, except we just have like this to deal with. So remember like how we dealt with like self-adjoint then was to multiply by like we divide by like the function here, make the coefficient 1. So it's like 3 on 5. And then integrating factor this. So like I'm just like see this out, like it's just equal to 3x5 minus lambda 5u x5 0. Then what I can do is I can just like compact like the first two into 3x5 u dash and like dash the whole thing minus lambda 5 u, okay, like ex5 and then u to this. So that right here is, oh, I missed something. Should be fine because this here, that's already in this form. It's like our p of x is clearly the e to 3x on 5. That's a u dash obviously there. We have a lambda here, so like lambda's arbitrary. And then this r of, that's going to be our r of x essentially. So yeah, we'll do the same thing. So yeah, that's going to be like our Sturm-Liouville form. Okay, so a regular Sturm-Liouville like eigenform is going to be like in like this general form. So L of u, it's going to equal to, so again, it's kind of like similar to like that eigenvector sort of notation. Like lambda times so v, it's going to be like our eigenfunction, like r, and then times it by u. And here's like our boundaries like the same. I guess like except like instead of saying alpha 1, alpha 2, you are saying like 0 essentially. Because I guess not like I want to deal with like a million different cases, I guess. Here, like whatever your P's are, the P is like in the Sturm-Liouville form. So like this thing here, like you're just assuming that's like not 0. So like you don't assume it's like singular kind of thing. Oh no. The value you sub it in is like not singular then. And you see me like the sum of like absolute value of these isn't 0. It's basically a guarantee that like if you have a look at this one, you're basically just saying like because like they all have to be positive. You're just saying at least one of them has to be positive. Like the other can be 0, that's fine, but like they both can't be 0. That's essentially what it's saying. Yeah. So, like the cool thing about the solutions of a Sturm-Liouville eigenproblem is that each of those eigen like solutions, they'll actually be orthogonal to each other, or essentially like when the integral is like root of 0. So another fact, I guess, is eigenvalues they get from Sturm-Liouville eigenproblem, they're always going to be real, assuming. Assuming that you use like real numbers, you should get real eigenvalues. If you involve complex numbers in your eigenvalue, I don't know about that. You could probably get complex values from what I'm guessing. Yeah. So once again, for like a Sturm-Liouville problem, most of the time you have like an infinite set of eigenfunctions, whatever acting on whatever interval you're working on, and like along your weight. And also the eigenvalues. So, like, let's say you had your first function. If you had like it have to be ordered. Yeah, let's just assume they're ordered. Like the eigenvalue for this, so this function compared to this one, the later values of the eigenfunctions would be like larger than that of the eigenvalues of like the previous ones. And notice here is like strictly greater than. So you can't like have equals kind of thing. Yeah. Okay. So consider this following ODE. So it's like the same one. On this interval, what equality must any of the two eigenfunctions for one obey? So it's really just remembering what we just said from the previous fact here, eigenfacts literally. Any two functions must be orthogonal to each other. So if we're like kind of like writing that in more like I guess like integral notation. So the inner product must be 0, or the integral from 0 to 1 of, let's just say u and v are like other functions, like u, v are eigenfunctions. Then the integral u of x and then v of x, let's just say r of x, just for the weight. Now that must equal to 0. That's the only like sort of equality you must satisfy, essentially. Oh wait. Okay, u and v. What's this? We see u v, that's the obvious. Then 3x 5 fifth. I'm guessing that is the weight function. Let's check. Sorry. I believe that's like. Oh wait, sorry. I believe that's like related to the Wait. I believe that's like related to this one here, because that is our Oh, what the hell? Oh yeah. So like that is our R of x essentially. Like like technically it's like negative. So like technically I really should have says like negative there. The way function the eigenfunction then it's a bit strange. Okay, yeah, but like it's gonna be like the negative of the integral or like who cares? It's just like the integral itself already is like 0. So like any two like 0 u and v, like as long as they're not the same, they just have to obey this. That's it. Okay. So now I'm gonna be considering how to solve partial differential equations, so PDEs, not ODEs. So consider like the temperature of like a bar length, and it satisfies this thing, like this differential property. So like notice here, like u, that's like is a function of x and t, but when you have like one t there, like on the subscript there, you're just diffing it once with respect to t. It's like partial diff t like that. So double x, that would be like diff squared over like dx squared, like that. Yeah. So like satisfies that, and like where like c is like some like arbitrary constant. And you have a bunch of like setups here essentially. So then additionally, we have this initial, boundary conditions. So you have t is equal to 0. You have x, it's like the diff is of like the length. Anytime t is equal to like some like negative of kappa multiplied by like a function like length of any time. So using the method of separation of variables and letting u go to this, like essentially like prove this, like derive these equations. So I mean it's already like kind of stated in the question. We're gonna assume that our function u is a product individually of x of x and t of t. So it's not like you don't have you don't have something like this because like you can't really write that as like a product of two like just a function of x purely and like function of y purely. So we're gonna be think of it as a product. So yeah, there's like the whole like name of like the purpose of separation of variables, like kind of like separating these. Here we can first diff our u of t essentially. So when we're partially differing this, like when we're differing like that doesn't matter. It's like a constant in the t world. But then when we're differing this, then that'll of course be like t dash in like the t world. So this will be like x of t dash, but then u of xx, that's equal to, so again, like we're diffing x this time, and we're doing double diff. So we diff x once, like x prime t, we diff x again, so it's like x double dash, so like x double dash t. Okay. And then we're going to use this fact here, link the two together. Essentially, xt dash was equal to c squared of x double dash t. Next thing we're going to do is divide or like just like force every like single like term like term like on its own side kind of thing. So like the t dash, like sure leave it. And then we're going to drag the t over. Let's just drag the c squared as well. And then divide the x over like here. Okay. So why do this? Because what we can see here is this is a function of t. So t dash over t c squared, that must be a function of t. Like it doesn't matter what t is, it just has to be a function of t. So there must be some function. There must be like some t terms in this side, or like some function of t. But I can say the same thing for the right side for x double dash and x. That is entirely involving x's, like whatever x is. The result must be also x's as well. So the left side must also have x's. So you might be feeling like, oh, is like some contradiction? Like, isn't like kind of impossible? The only thing that can make that possible is constant itself, because like obviously a constant is a function of like whatever variable you're dealing with. Like if this indeed was like t, if there was like t, some function of t's here, like this side wouldn't really make sense. Maybe if you have something like 5, like that would make sense. And like same for the other side. Like if the left side is also 5, that's also like fine. So the only way to make this like work is each of these must be equal to some like specific arbitrary constant. So essentially we're letting this equal to k. So like it doesn't matter what k is, but what can we do from here? Well then individually, let's just focus on like the t's. So t dash is equal to kt squared, and then just like rearranging, it's like minus c squared kt is equal to 0. Okay, they flipped around, but like whatever. Other side kx, and then k dash minus kx equals 0. So that's how we can like divide these ordinary equations. So essentially we just turn the question from a PD into like two ODEs, just for the purpose of separation of variables. Are we solving this? Okay. Alright, so what boundary we said that, right? Yeah. What boundary conditions must X satisfy? So we already know that this sort of ODE must be true regardless, but we just have to make sure that it's in line with this here. So how can we show that works? So I guess like the first thing we can do is we can like legit just solve it. So okay, well, like since we know like u is equal to x of t times t of t, we can just sub in like what we just have. So like I guess like x of 0, t of t must be equal to 0. And then solving the other one is like x of L, t of t must equal to the negative of kappa of t of L, t of t. Okay. So the important thing here is that if we want t, if it was a trivial solution, I mean it's a bit boring. So we don't want to assume that. There can only be one thing, which is the fact that x of 0 must be equal to 0. Okay, so like, we're going to use that fact later. This thing here, we can like move to the other side. Then from here, so notice how there's like a t of t in like both of them, but once again, assume that it's not the trivial solution to make it like less boring. So we're essentially saying x of L plus k of t of L. No, let's not mess that up. That's meant to be an x. Okay. XL is also XL. Okay, so like that. So from here, that must equal to 0. Okay, I'm getting, I think like, I know dash, sorry. Dash of it is like x dash L. So that's still dash, that's dash. So, like, yeah, we just have like this essentially. Just double check. Yeah, okay. So, like, if t is, if t isn't the trivial solution, these two conditions, these two conditions must hold true. Okay, so that's the conditions that x has to satisfy. Okay, show that in the case of k is greater than 0, only trivial solution exists. So we have to, what is it? Oh yeah, okay. It's like working from above, like we had this. So it's essentially saying like when k is like positive. So we need to solve this ODE in terms of x's. So call that x. It's like the equation related to is like r squared minus okay, well first we have to do one more thing, which is that like when your k is positive, so we're gonna let k equal to mu squared. So like that's definitely fine. Like mu is like just assume it's okay, like it can't be positive or negative then. So it's like this. Then the solution is associated to this. So it's like r squared minus like mu squared. So it's like plus or minus mu, or just x is equal to c1 e to the mu, dealing with x's here, right? So yeah, x plus c2 e to the minus of x. So that's gonna be like the general formula, but we just need to now like make sure like it's in line with this essentially. So when we sub in x is equal to like little x 0, big X is 0, so it's like c1 e to the 0, so 1 plus c2 is equal to 0. It's like the first condition. Second condition. So okay, like I put this in brackets, like x dash. C1 mu e to the mu, we sub in L, minus C2 mu e to the minus mu L. So that's our x dash L plus kappa, and then we just sub in L as usual. So like e to the L plus kappa C2 e to the minus mu. That. So what can we do from here? First condition, we can kind of conclude like C2, it just has to be the negative C1. So it's kind of easy. So we can see that C1 mu E L, I don't know why I did a minus. Oh yeah, so like at this point here, the minus C2, I can replace that with just C1. So like I'm doing plus C1 mu e to the minus mu L plus kappa C1 e to mu L, because C2 again, like the minus C1, so I'm going minus k C1 e to the minus mu L. Okay. Notice how there's like a C1 in every single term. So the big kicker here is I'm going to say assume C1 is not negative. Okay, because I'm trying to like prove it's not the trivial solution, hopefully. So if that's the case, I can just divide by C1. So in that case, what do I get? I can factorize a bunch of terms here. So okay, I'm gonna like focus on this and this. So like the e to the mu L. The e to the mu L, the coefficients are like mu and kappa. So mu plus kappa. And then I'm going to plus other ones, like e to the minus mu. Coefficient of those was like mu. This is a minus, so minus k. So from here, then I can like move this term to the other side. So like e to the mu L. Okay, let's just swap this around. So that's fine. And we have e to the minus mu L. And then when this gets like moved to the other side, it's like a negative. So like just negate the whole thing inside. It's like kappa minus mu. And then what we see there, we can do two things. Get this e to the minus mu L, times it to this one, so it becomes 2 mu L, and then divide this kappa plus mu to the bottom. Okay? So from this point, what can we conclude? Like it doesn't seem like there's anything like that seems wrong so far. But here's when you be like me, I guess like think more creatively. So mu, that has to be greater than 0. So is L. Those should make sense like the physical sense, at least for L. Yeah, it says somewhere here. Okay, I guess it doesn't say it. So like you think about it. Like mu is greater than 0. Like we're just thinking like mu is like just assuming like it's not negative essentially. And then for L, like it has to be greater than 0 because like the length of the bar can't be negative. So this like argument side has to be greater than 0. So consider e to the x, because e to the x itself is like it's still positive. It's still positive, like regardless if it's negative. But if x is strictly positive, what that means is the output of e to the x that actually has to be greater than 1. So essentially, what we're kind of prove is that e to the 2 mu L that has to be greater than 1. Okay, so that's just like the arguments on like e to the x. But what can we do with this side? So this side, I'm going to say like a really obvious fact. So I'm going to be kind of like working backwards. Mu is greater, negative mu is less than like mu, essentially like that. Again, like because mu is positive, so it's definitely greater than it's like negative counter. Now what I can do is like I can just like add on a kappa to both sides. So something like that. That's not be true. But then I can divide by kappa plus mu. Again, that's fine because both of these are positive. So I'm not going to like divide negatives to flip the inequality. So this thing is less than 1. But now there's a problem because this thing here has to be greater than 1. This thing here has to be less than 1. So that's a bit of a problem then. So at this point, we reach a contradiction. So essentially, like we made a wrong assumption. What was that wrong assumption? It was this here. Assuming that C1 is not, let's say 0. Assuming C1 is not equal to 0. That's the assumption that was wrong. So once our contradiction was wrong, then we see like, okay, C1 has to be equal to 0 then. That's the only way to make this like sort of work. In that case, well then C2 has to also equal to 0 because like remember it's like the negative of it. So it's still obviously 0. So C1 and C2 are both 0. So then the only way to like kind of make this work for X is at least when K is greater than 0 is only the trivial solution, or like when it's like X is 0 kind of. Yeah. Okay. Next, show that when like K is equal to 0, only trivial solution exists again. So like once again, like that formula X minus KX 0. Well then K just like makes it go away. It's like X double dash is 0. So like the general solution to this is like a linear function. So X is equal to AX plus B. But once again, we like make sure this is in line with our conditions. So like from my memory, like X is 0, 0. I forgot the other one there. Yeah, so again, like satisfy these conditions. When we sub in 0, what we see is like 0 is equal to sub in little x0, it's like 0 plus b, but then b 0. So that's gone. But then when we try and like make this one here, x dash, so x dash is just a, so just a plus k of xl, so sub in the l there. So al is equal to 0. Factorize in a plus k0. So once again, we have to kind of like use raising here. Let's assume again like a isn't 0. Well then 1 plus kl, that must equal to 0. Well then kl must be equal to negative 1. I'm hoping that, yeah, okay. Because kappa here, it's positive, but then L is also positive, again, because like the physical length. So there's no way it can be negative 1. So this like conclusion is definitely false. The only way to make this true then is if A is 0. So A is 0 and B is 0. So once again, like we kind of just like conclude like it's just a trivial solution again. However, the last case like provides hope. So when K is less than 0. So if that's the case, we're going to say, I'm going to run out of space. I'll just do it here. So essentially, let K to the negative of the mu squared, just so like we're not dealing with like i's and all that. So we have K, x double dash plus mu squared is equal to, x double dash plus mu squared x is equal to 0. So once again, you have like the I roots kind of going on. So the general solution to those is x is equal to c1 sine of like the roots like mu, so it's like mu of x plus c2 cos of mu x. So again, like for like the third time, just make sure this like is in line with our conditions. So x is 0, 0. You sub in x is okay. So like first one, 0 equals to sine 0 goes away. C of 2, so it's like C of 2 is 0. So yeah, C of 2 is 0. So already not off to a good start. Only hope left is like the C1. So literally like the x dash thing. So x dash L, okay, plus k of xl is equal to 0. So how do we do this? So like at this point, like our solution just only consists of C1 sine of mu x. We have no C2 to deal with. So when we're diffing that, it's like mu C1 sine of mu L plus k of xl, so like sub in L's fine. So that, and then that thing has to go to 0. That should have been a cosine. This is cosine. Yeah. So we just need to do rearranging, see like maybe any contradictions were going on. So what we can do is like kc1 sine of mu L is equal to the negative of mu c1 cos of mu L. Once again, let's assume c1 is not 0. Hopefully it's not the trivial one. So we're just left with k1 sine of mu L is equal to the negative of mu cos of mu L. So let's do two things. Divide by cos and then divide by kappa. Okay, that's not really meant to be in here. Tan of mu L, so sine cos, to get the mu of negative mu on k. So what does this provide us? Essentially, there are other solutions for mu that makes this work. There actually are solutions. So if you kind of think about it, like if you do graph this looks like mutes of x kind of thing, it looks like this. Like the tans look like that. It's like infinite of them. But then the negative mu on k, it's like a linear line. So it's like it's the negative gradient. So what you'll see is like obviously I'm like limited by my like finite space here, but there are an infinite number of solutions that will make the line intersect with the tan graph. So there are an infinite number of solutions. So like essentially what you can do is basically just say like what we found is you don't have to restrict C1 to 0 anymore. We haven't reached that contradiction or conclusion anymore. We can make this like sort of like when we like factorize like C1 like the other side. In those like last two cases, like this thing was like absurd. There's no way they can make it happen. In this case though, you can make that happen. So C1 doesn't have to be like 0. Like obviously the trivial solution would work. But I'm just saying now it's like there can be a non-trivial solution. So for this one, there would exist infinite number of mu's that will make this work. Obviously, though, like we can't really find mu because like an explicit formula because it's kind of like trapped inside of a tan. So like I don't know how I meant to like tackle this. So really, the only way to like find is just like numerical methods or whatever, just like estimation. But we know they exist, and that's the main point. So let's say like mu of n, that is going to be the nth solution to like whatever this like tan equation is. So by that logic, then x, just x, not xn. Yeah, x is equal to sine of, well, mu, which let just be like that mu of n solution, mu n of x. So that is a solution. We're not, like it just says here, there exists a non-trivial solution. Like, we don't need the C1, but like we would need a linear anyway. But like whether they have the C1 or not, like it's not like a matter in this question. But yeah, that's how you like, do this one. Yeah. Okay, so find all the possible solutions of T of nt. So yeah, like, we're just gonna use this like what do you call it? I guess formula here. The T dash is minus kct squared, kc squared T is equal to 0. So like there's like a whole different like methods. Yeah, let's do integrating factor. Okay. Kc is equal to 0, then like this diff is equal to 0, and then case equal to t is equal to say constant. T is equal to a of e to the kc squared. There should be Why isn't there? It's a constant. Wait, where the t's at? I'll be like stumped here. Oh no, there's meant to be a t in each of these integrating factors. Yeah, I forgot that. My bad. But yeah, that is going to be our like general solution here. But we got to do this in terms of our because like okay here, like again, like if it was if like k was like greater than 0 and all that, like we did like the trivial solution is like boring. We're not after that. After the case when like k is less than 0, that's the one we got like an actual solution. So remember the set in that case like k is equal to like minus mu squared. So actually no negative here because I brought it to the other side. But when k is equal to minus mu squared, that's the one we call actual solutions, then we find like t is equal to a of, so we did find a mu that did work. So whatever that mu was, like, let it be like that m solution. It's going to be this essentially. Squared c squared t. So that's going to be our, essentially like our general solution of like t. So find the general solution of u. So remember that u, that was equal to the product of like each of like the x of x's and the t's of t's. So the product of them is our solution. So essentially it was for x, I believe, I'm just copy it. It's like sine of mu n x and then our t. That's our like the one here. Ignore this like a thing for now. E to the minus mu n c squared t. So that's the product of it right now. And so if we're asking for all solutions, so remember for like for what Brendan said for like topic 1, any linear combination of these solutions will work. So that's like when you have like a factor in and then you like sum of all of them. So we can just like say like c of m as like the factor, and then you have the sum. So you just have like I ends 1 up to like, is there even a limit? Okay, you have like infinite. So that is the general solution here. So it's like the product and then just like factor here and like just linear combination. Yeah, and like specific, you have to specify mu of n. So just the solution of this essentially. So that's how we tackle this PDE, honestly. So not too bad. So yeah. So that there's like a 1D IBP though, because we're only working like sort of like one dimension. And like we have like just a rod like that. But we have like a 2D IBP. It's kind of similar really. Like you are again like considering like the separation of variables. Actually, what's the difference? Well, no, it's like the same thing, really. Yeah, okay, no. Okay, elliptic operators. So you can write PDEs in this sort of general form. So LU, that is equal to the negative of, like, you got like a double sigma because you can represent, okay, like, you can have, okay, like U of XX. Okay, you differ with respect to X, and then you like differ with respect to X again, or you can do like U of X like Y, something like you have like this argument, this argument. So you have like two like things to deal with there. That's why you have the double sigma. So importantly, you can have like a coefficient in front of like our like diffs essentially. So it's like our second order diffs essentially, but this is like our first order diffs. So just differ with respect to one variable, so maybe like ux, uy, uz, and then here like just like any like function like times by like u essentially. So essentially, actually wait, one more thing. Like A, that's going to be the matrix formed by like whatever the coefficients of these are. So for our second order diffs, that is. So show an example later. But specifically, second order PDE, it's called elliptic if like on our region, whatever it is, if there's a specific positive C value such that for any x within our I guess like a domain or whatever, and our like xi for like domain for like the d like the reals for like the dimension d, then like the transpose multiplied by the matrix of like some like vector, and then multiply with xi again, it's greater than xi or c, like that constant c multiplied by xi squared. So it's like the norm squared of it essentially. So again, we'll do an example here. So this PDE is this elliptic. So we need to recognize like the formula it's in. So all of these are like second order like gifts essentially. No like the stuff like that's kind of gone. But notice how we have like this negative here. Yeah, the negative is kind of funny. I don't know why it existed in the first place, but so what it is like we need to like make sure like get the negative out there first. So like factors the negative. So like 5uxx u of xy minus 2xz minus uzz. Okay. So then we're going to be using this fact here. A is the metric formed by the second order coefficients. So like how you should be thinking about this is how you should be like reading this kind of is like this is the coefficient of like uxx. This is the coefficient of uxy. This is like the coefficient of like uxz. Then the next line is we're gonna do this. Sorry, we're gonna do that one because like that would just be uyx, but then that would just be the same with that because like I believe like the mixed derivatives theorem. So you don't need to deal with like the ones below the diagonal at that point. This one's like uyy, this is like uyz, and like the last one's gonna be like uzz. So that's how we should read the coefficients here. Of course, like if it isn't mentioned, like in our form here, it's gonna be 0. So using that form here, uxx, so that's our first one, it's 5. Uxy is 1. Xz is 2, negative 2. Uy is gone, but then uzz is like negative 1. So what we have here is this matrix here. 5, negative 1, 0, 0, 0, 0, 0, negative 1. So how do we like sort of bring this in here? Essentially we need to like let xi equal to basically like xi 1, xi 2, xi 3, kind of like that. Yeah, I'm just doing those letters. So like the transpose is like on like that 5 1 negative 2 0 0 0 0 negative 1 and like the vector itself here. So I'm here like the matrix multiplication of that. So 1 by 3 and 2 by 3. So should we get like a 1 by 3 at the end? So we get like 5 xi 1 xi 1 again minus 2 xi 1 minus xi 3. Okay, I have to use a space. So xi 1 3 multiply that by xi 1 xi 2. I'm getting really lazy this numbers. So it's like the first one's like 5 xi 1 squared plus xi 1 xi 2 minus 2 so wait. Oh no, this is like one thing. Okay, wait. Okay, so like that, and then this minus 2 xi 1 xi 3 minus xi 3 squared. Okay, like that lines up with this, so it's good. So essentially, like you can do this really easily if you prove that this thing is negative some specific choices of your xi's. So let's say in this case, xi 1 is 0, xi 2 is 0, xi 3 is like 1. So why do that? Because xi 1 squared, I'll just go away at 0. Xi 1 is all 0. xi1 will also make it 0. But this thing is 1, so like -1, essentially. So what we just found is that this thing, like this expression, what we have, like the specific choices we made for xi, that is -1. So we're saying that this thing is like negative then, which is, we can't make this true then. Like it can't be greater than like a positive value then. So that's like an impossible case. So essentially you just found like a specific value so that it's like less than 0. So it's definitely not elliptic then, according to this definition. If the result was something like xi1 squared plus, like basically like if the right side is definitely positive, regardless of what choices you have for your xi, then you can then at that point like guarantee it's like elliptic. So that's how you like tackle that essentially. Okay, almost done. All right, so divergence. So this is kind of like getting to like 2 1 1 territory. Be like Donna course. So let like that essentially equal to like the partial derivative with respect to your ith component. So like a scalar field is like a scalar field is when you have like you're inputting many different vectors. So like f of x y is equal to x squared plus y squared. Like you're inputting multiple things, hence it's like Rn, but what you get out is like a single number. It's like that's like a number, so you don't get like multiple outputs. So what we're going to define the gradient as of your scalar field is we have this thing called nabla, so it's an upside down triangle, but then that thing compacts the information of this, where it's equal to like the partial diffs back to like each like component essentially. But then this thing is definitely a vector. That's not a number anymore. But then for a vector field, so a vector field is when you still have an input like x and y's, but you might get out like a vector. You'll get out a vector essentially. So this is no longer a number. It's now a vector. So like -1, 2, whatever. We're going to call the divergence of a vector field is going to be defined as nabla dot product with our f essentially, our vector field. So it's essentially like this thing, like the partial diffs, like partial diff like that, but you not times, but like you apply it to each of your ith component of your vector field. So like maybe like in this example, I'd apply the first component, in this case maybe x, I diff this, the first component with respect to x, and then get like the second component, I diff that with respect to y. So that's kind of how you define the divergence. The divergence, though, like you input a vector field, it's like R of n. You also get out. No, you also get out a number though. So this again is like a number. It's not a vector field. So essentially, what this is saying is we can represent our operator in terms of this like divergence form. So it's going to be the negative of our nabla dot product with some vector, so not vector matrix, and then multiply by like the gradient of our some vector here. So if that's the case, then if u is like a function of two variables, write this second order PD in like the specific like divergence form. So what we can recognize is like this this expression there. That's our L view, but then this e x plus y. So that's like a that's the forcing term. So we just ignore that. So this thing here, this is our I call it like the OU expression, but we need that expression to equal to this essentially. So this thing is ultimately equal to like this number like top product or that. Firstly, like I guess like the negative might be throwing us off, so we just write this like negative x u x x minus y squared u y y minus ux minus 2y uy. So like a lot of negatives. But you recall that from like actually wait, like this is the so like the nabla dot product with so this thing that should be a vector field, like as stated like this, like f inside is a vector field. So essentially like what this is saying on the left though is that that's equal to, because we know what the actual components are. It's like partial with respect to x. I might as well just say what's that notation I said? Okay, I'm just saying 1 and 2. Like it's like 1 is corresponding to x, 2 is corresponding to y. partial diff of here's the problem, because we don't know what like our f, that is like the product of our matrix, because the whole point of this is we're trying to find a matrix A to essentially make this work. Why isn't like divergence form? So we don't even know what this like matrix form is, and like what's up. We don't even know what the product of this is. Let's just say that for now, A of mu u, that's equal to some vector. So that's a matrix multiplied by a vector. Let's say it's 2 by 2. So 2 by 2, 2 by 1. So it is 2 by 1. So like this is a vector here. So let's say that, and that's still a vector field. So that's fine. So it's like, okay, I'll just say x then. The partial diff of x of A plus the partial diff of y to B is equal to like this thing right here. Like, that's what we have. Okay? So we're trying to match up the how do we proceed from here? We're trying to match up specific parts, like relating this question here somewhat. Kind of sounds a bit vague, but let's notice this here. Let's rearrange this into okay, minus xux minus ux, and then minus y squared uy minus 2y uy. Who cares about dx plus y? So actually what we're trying to look for is we are trying to find an expression of, we need to find the partial with respect to x of some expression plus the same thing for y. Notice what's going on here. Pay attention to this, because we can notice how it's like, it's very resemblant of like a dot product thing going on. This in fact is I'm going to change to say this with respect to x, because this thing when we diff that's equal to minus ux, but then diff the other thing, because like product rule, that's going to be minus x uxx, which is what we have exactly. We just swapped it around, but that's what we're after. The diff of like some specific expression. This is that expression that we're after. Very similar for the other one for y. So I believe for that it's like negative y of uy. So that's exactly what we're after, because then we can exactly find what a and b are. So just from this, I just like equating coefficient, not coefficient, but like just equating the terms. Like a is equal to negative x of ux. B is equal to negative y, that's y squared. Y squared uy. So that is our a and b terms. So kind of to like say that here, this a of times like nabla u, that's equal to, we can actually write it our actual terms. U of x minus y squared uy. That's that. So how do we proceed from here? We still need to find the matrix A, but here's the thing. We know that nabla u, that must equal to like the gradient, like this thing here, or essentially just like partial diffs of like our function essentially. So we set our kind of function, this one's like u, that belongs like the L of u. So like obviously u of x, u of y, they represent like the partial diffs. So nabla u is equal to u of x, u of y, again, because of like this essentially. So we just need, at that point we're like really close. We just need to find, okay, matrix A multiplied by u of x, u of y, must then equal to, I'm really going to run out of space. It's equal to minus x ux minus y squared uy. So it's that. Then how do we find the matrix A? So I'm going to say like the matrix representation form or something, like the theorem, something like that. But essentially it's like, so I think like linear algebra, like 1B, where you had like, oh yeah, like the linear map is like 2a plus 3b and like minus a minus 5b. Then like what's like the matrix to represent the transformation? It's like you just read off the coefficients essentially. If you know like the matrix multiplied by ab is equal to this. So it's like you literally just read off the coefficients. It's like 2, 3 minus 1 minus 5 and like times like ab. That's the I think that's the matrix representation formula, theorem, something like that. So it's the same idea here. I just realized I can write on the right the whole time. You can kind of think of this as like minus x ux plus like 0 of uy, and then 0 ux minus u squared uy. Okay? Because then what you can say is like, again, like kind of like the method of what I just did there, just read off the coefficients. You just get minus x, minus y squared, 0, 0, and like ux. Just tag on this at the very end. And guess what? This is exactly the matrix that we're after. Like this thing is definitely nabla u. So what we just have remaining is just the A. So that's what we just what we're after. That is our matrix A. So like putting it all together then, where is it? LU, that's equal to the negative of the nabla of A. So minus x minus y squared is 0, 0. And that thing's like, do I have to say, I just say nabla u, yeah. Yeah, okay, nabla u. Yeah, like that. Okay, but I have to be careful with like this. Because this is like dotted with that matrix. Yeah. So that is how we derive our matrix here. So yeah, that's basically that essentially. Yeah, we just found a suitable A to like essentially make this work. So okay, like one more thing, like the e to x plus y, so you have to say that. So it's like the nabla is equal to that. I'm sorry. The LU is equal to this. It's like the nabla, like dot product, like all this stuff here. And yeah, that's how to answer this question essentially. So yeah, essentially that should conclude the seminar. And yeah, yeah, I hope everyone does one exam. Should be chill, not gonna lie. Yeah. All right, thanks.